The first impression of a lionfish is almost hypnotic. Suspended in the water column like an ornamental tapestry come alive, it moves with the kind of slow, deliberate grace that suggests absolute confidence. Its fins do not merely sway, they unfurl like feathered fans, striped with patterns that mimic fire overlaid on white silk. In bright water, the fins ripple outward into a halo of spines and membranes, giving the animal a theatrical presence far larger than its true body size. From a distance, it looks harmless, almost delicate, as though it were crafted for an aquarium display rather than shaped by natural selection. And that illusion is precisely why so many divers, snorkelers, and even trained photographers drift closer than they should, inching forward with cameras extended or gloved hands outstretched, believing that something this beautiful must also be safe to approach. Yet beauty in the ocean often hides a deeper set of evolutionary calculations. The lionfish, despite its serene and ornamental appearance, carries along its back, sides, and belly an arsenal of venomous spines designed to discourage predators with decisive efficiency. These spines are not merely sharp. Each sits atop a channel that delivers venom into anything that presses against it. When the spine punctures flesh, the skin around it ruptures slightly, and a sheath surrounding the spine compresses upward, forcing the venom deep into tissue layers. The process is swift and mechanical, requiring no intention from the fish. The lionfish does not lunge or strike. It only needs pressure, a hand brushing against a spine, a knee planted too close, or a diver misjudging distance while adjusting buoyancy. The venom's purpose in nature is purely defensive, a warning system that ensures predators learn quickly that a lionfish is neither easy nor worthwhile to swallow. Once inside human tissue, the venom acts with a complexity that often surprises those who experience it. The first sensation is a burning heat, as though the flesh beneath the skin were being heated from the inside out. Swelling follows in minutes, sometimes expanding enough to render a hand, foot, or forearm nearly immobile. The pain intensifies rather than fades, radiating up nerves and triggering a cascade of inflammatory responses. Victims describe the sensation as deep, throbbing, and unrelenting, often lasting many hours even with treatment. In severe cases, especially when multiple spines puncture the body, systemic symptoms can emerge: nausea, dizziness, sweating, and in rare instances, difficulty breathing as the venom interferes with muscle contraction. The venom itself contains proteins that disrupt ion transport in nerve cells, effectively scrambling the signals that dictate sensation, movement, and pain. The body responds with swelling in an attempt to dilute the toxins, but this swelling also compresses nerves and exaggerates the sense of pressure. For many divers in the Atlantic and Caribbean, these stings are not the result of careless contact, but part of the broader ecological story unfolding across the Western Hemisphere. Lionfish, originally native to the Indo-Pacific, have established themselves with alarming speed throughout warm Atlantic waters, from the Bahamas to the Gulf of Mexico and down through much of the Caribbean basin. The exact origin of this invasion remains debated, with theories suggesting aquarium releases in Florida several decades ago. Regardless of the starting point, the impact is undeniable. Lionfish reproduce rapidly, with females capable of releasing tens of thousands of eggs in buoyant mucus clusters that drift effortlessly with ocean currents. These eggs hatch quickly and disperse widely, allowing juveniles to settle across vast stretches of reef habitat. With few natural predators in the Atlantic, lionfish populations surged. Their hunting strategy, refined in Indo-Pacific ecosystems where competition is intense, translated perfectly into the new environment. Lionfish approach their prey slowly, spreading their fins outward like a living net to corner small fish and crustaceans against coral, sponge walls, or the seafloor. Their strike is rapid, a sudden forward thrust followed by a powerful suction force that draws prey into their mouths before escape is possible. This combination of deceptive calm and explosive precision makes them highly successful hunters. On many invaded reefs, lionfish consumption has reduced populations of small native fish that play essential ecological roles, such as cleaning algae and grazing overgrowth. Without these grazing fish, algae can smother coral, destabilizing the entire reef system. Recognizing the ecological threat, divers and conservation groups across the Atlantic began targeted removal campaigns. Spearfishing lionfish became a conservation act, not a sport. Volunteers equipped with pole spears or specialized containment devices began descending onto reefs to remove as many lionfish as possible. Yet even during these removal efforts, the fish's venomous spines continued to injure divers. Thick gloves offered some protection, but lionfish spines are sturdy, and in several documented cases they pierced directly through protective gear. Some divers experienced stings even after the fish had been speared, since the venom remains potent long after death. Handling the fish requires precision, awareness, and secure containment, because even a slight slip while placing it into a catch bag can lead to a spine puncturing an unwary hand. What makes lionfish particularly dangerous is not aggressive behavior. They are far from confrontational, but the combination of slow movement and fearless approachability. Most venomous animals rely on warning coloration or rapid escape responses to avoid accidental contact. Lionfish, however, swim deliberately, almost inviting attention with their extravagant fins and lack of hurry. They are accustomed to having predators keep their distance in the Indo-Pacific, and they behave the same way in the Atlantic, unaware that curious humans do not interpret their confidence as a sign of danger. Underwater photographers often drift close, entranced by the fish's ornate patterns and steady poise. They frame shots from all angles, forgetting that the 15 or more spines radiating from the fish's body are rigid, sharp, and capable of penetrating bare skin with surprisingly little pressure. A photographer adjusting position in surge or current only needs to misjudge distance by a few centimeters to find their hand pressing inadvertently against a spine. This slow, composed behavior is itself a biological adaptation. Lionfish rely on their appearance to intimidate potential predators, making themselves look larger and more dangerous than they truly are. Their fans of fins exaggerate their outline, while their spines signal a clear warning to any animal that has learned the cost of attacking one. This strategy works effectively in the Indo-Pacific, where predators such as large groupers, eels, and certain sharks recognize the threat and keep their distance. In the Atlantic, however, predator recognition is limited. Native species did not evolve alongside lionfish and therefore do not instinctively avoid them. Still, despite occasional reports of sharks, snapper, or grouper consuming lionfish, these events remain rare and inconsistent, leaving human removal efforts as the primary control measure. The ecological consequences of the invasion reveal how interconnected marine systems truly are. By reducing populations of herbivorous fish, lionfish indirectly influence coral health. By consuming juvenile fish of dozens of species, they reshape food webs. Their ability to thrive in a wide range of depths, from shallow mangroves to deep reef walls, gives them access to nearly every corner of the ecosystem. Even their reproductive strategy is built for expansion. Females release egg clusters enveloped in a gelatinous coating that protects them from many predators and environmental threats. The eggs drift long distances, allowing lionfish to colonize new habitats rapidly. Once established, they display remarkable tolerance for temperature, salinity variation, and habitat complexity. Understanding lionfish also requires understanding why they continue to attract human fascination, even in places where they pose a threat. Their appearance is unlike most reef fish, with bold stripes that catch the eye and fins that mimic ornamental plumage. Their calm demeanor gives them an almost regal presence underwater. Many divers find themselves drawn in by the quiet authority of their movements, unaware that those same movements evolved to advertise danger, not invite contact. The lionfish's beauty creates a false sense of safety, and its slow approach gives people time to convince themselves that touching or closely observing it is harmless. For every diver who keeps a respectful distance, there is another who leans in just a little too far. The inherent tension between beauty and hazard defines the lionfish's place in human perception. In an aquarium, behind glass, its fins are admired without risk. In the wild, the equation changes. Here, the patterns and spines represent millions of years of evolutionary negotiation, a system built to communicate "do not touch" to predators capable of causing serious harm. The tragedy is that humans often misinterpret visual cues designed for completely different species. The spines that signal danger to a moray eel or a hunting jack mean little to a snorkeler who sees only color and symmetry. As the sun sets behind a Caribbean shoreline and the reef slips into twilight, lionfish remain active, drifting between coral heads with the same calm precision that defines them in daylight. Their silhouette against the fading blue carries the unmistakable outline of their ornate fins, each spine standing ready to defend against any creature that underestimates the cost of contact. The ocean is filled with predators that announce their power through speed, size, or violent displays. The lionfish takes the opposite approach. It moves slowly, glows with beauty, and waits for others to come too close. In this quiet confidence lies its true hazard, a reminder that in the natural world, danger does not always arrive with aggression or noise. Sometimes it floats gently, adorned in stripes and feathers, waiting for curiosity to do the rest. In the calm shallows, where seagrass sways with the unhurried rhythm of the tide, a small pufferfish drifts between blades of green, like a wandering ornament carried by invisible threads. Its rounded body, soft eyes, and hesitant fin-fluttering movement give it an appearance closer to a toy than a predator or a threat. Sunlight flickers off its speckled skin, and at times the fish almost seems to hover in place, as if contemplating its next move. This gentle, almost clumsy demeanor is precisely why snorkelers often pause to admire it. Children trailing behind their parents point excitedly, perceiving it as one of the harmless curiosities of a shallow lagoon. Even adults feel the pull of its cartoonish appeal. Yet beneath this disarming softness lies one of the most potent neurotoxins found in the marine world, delivered not through dramatic strikes or venomous spines, but through tissues that appear benign, edible, even inviting to those who misunderstand the danger. The toxin inside a pufferfish is called tetrodotoxin, a compound so potent that even amounts too small to see can interfere with the most critical electrical processes in the body. Tetrodotoxin binds to sodium channels in nerve cells, effectively shutting down the pathways that allow nerves to send signals to muscles. Without these signals, muscles cannot contract. This includes the diaphragm, the sheet of muscle that drives human breathing. When tetrodotoxin enters the bloodstream, paralysis spreads methodically. Lips numb first, then fingers, then legs, until the chest itself stops moving. Victims remain fully conscious during this progression, an experience described in medical records as one of the most haunting forms of poisoning, because the mind stays clear while the body becomes immobile. The toxin does not cloud thought, it erases control. This chemical weapon does not come from the pufferfish itself, but from symbiotic bacteria that live within its tissues. Through evolutionary partnership, the fish has become a carrier of bacteria-produced toxin, several times more powerful than many forms of venom found in snakes or marine predators. The puffer uses this toxin as a defensive tool rather than an offensive one. It cannot outrun many predators. Its swimming style is slow and imprecise, powered by small pectoral fins that flutter but do not provide real speed. Instead of fleeing, the puffer inflates its elastic abdomen with water or air, transforming from a compact fish into a spiked sphere too large to swallow. The toxin in its tissues teaches predators that even if they manage to bite through, the cost will be catastrophic. This evolutionary strategy blends mechanical inflation, visual deterrence, and biochemical defense into a single system more sophisticated than its cute appearance suggests. Humans have learned this lesson repeatedly across centuries, particularly in regions where pufferfish have been consumed as delicacies. In Japan, the dish known as fugu occupies a place of cultural significance, celebrated for its rarity and the precise skill required to prepare it safely. Only chefs who complete years of rigorous training and licensing are legally permitted to serve it. Their training involves detailed knowledge of the fish's anatomy, including which organs contain the highest concentrations of tetrodotoxin. The liver, ovaries, and skin can hold amounts potent enough to kill an adult, even in minuscule quantities. The removal of these organs must be exact, leaving no residue, no accidental tear, and no contamination of the edible portions. One misplaced cut, One slip of a blade can turn an expensive, revered dish into a lethal mistake. Cases of fugu poisoning have been documented throughout history, often occurring not in restaurants but in homes. Skilled preparation gives fugu its prestige, but the danger attracts amateur cooks who assume that careful slicing alone is enough to neutralize risk. Stories emerge each decade of individuals who attempted to clean and cook wild puffers they caught themselves, or who purchased the fish without understanding which species were safe. Many of these cases involve individuals who tasted only a small bite before paralysis began to take hold. The progression is predictable. Numbness spreads across the lips and tongue, followed by a sense of floating detachment as the toxin interrupts nerve conduction. Breathing becomes shallow, then impossible, and without immediate medical intervention, suffocation follows. Even with ventilation support, recovery requires hours, sometimes days, as the body slowly metabolizes the toxin. The danger extends beyond traditional cuisine. Fishermen handling nets sometimes suffer small cuts on their hands that allow tetrodotoxin to enter through broken skin after touching puffers caught unintentionally. In some coastal regions where pufferfish density is high, bites or accidental handling injuries contribute to a steady stream of mild to severe poisonings. The toxin does not need ingestion to cause harm. Tiny abrasions are enough for molecules to slip into the bloodstream. This is why coastal safety guidelines emphasize that a wild pufferfish is an animal to admire from distance rather than touch. Its soft appearance, rounded body, and seeming harmlessness disguise a chemical potency that surpasses that of many well-known venomous species. In the wild, puffers play an important ecological role. They graze on algae, sponges, and small invertebrates, maintaining balance within reef ecosystems. Some species feed on toxic prey themselves, absorbing additional compounds into their tissues, which reinforces their own toxicity. This cycle of consumption and accumulation creates a feedback system where the puffer serves as both a predator and a repository of chemical defenses acquired through diet and bacterial symbionts. Their unique teeth, fused into beak-like plates, allow them to crush shells and scrape surfaces with surprising efficiency for such slow swimmers. This grazing behavior influences the structure of reef communities, controlling the growth of certain organisms and preventing competitive dominance by algae or sponges. The inflation mechanism, often seen as a comical display by casual observers, is actually a complex survival adaptation. The puffer's skin and abdominal cavity stretch to multiple times their resting volume when the fish rapidly gulps water into its stomach. Muscles along the stomach walls contract to force the water outward into surrounding tissues, giving the fish a spherical shape. This transformation increases its apparent size dramatically, making it difficult for predators to swallow. Some species add a second layer of deterrence by erecting small dermal spines that protrude only when inflated. These spines are not venomous, but combined with tetrodotoxin, they form a powerful warning system. Predators that attempt to bite an inflated puffer risk choking, puncturing their mouths, or experiencing fatal poisoning. Yet it is the human relationship with the fish that creates the most dramatic narrative. People remain drawn to dangerous animals when those animals appear harmless. The puffer's large eyes and timid movement make it seem approachable, especially to inexperienced snorkelers. Some attempt to provoke inflation by chasing or lifting the fish, unaware that such harassment can injure the animal severely. Puffers struggle to expel swallowed air if lifted into the atmosphere, leading to internal damage or death if they cannot re-establish pressure balance. A fish that inflates defensively above water may never fully deflate again, making human curiosity not just risky for the handler, but devastating for the fish itself. There is also a global context to consider. Pufferfish poisoning occurs in coastal regions across Asia, Africa, and the Middle East, where certain species are consumed traditionally or caught inadvertently in nets. Even when cooked, tetrodotoxin remains stable because heat does not break down its structure. Boiling, frying, or drying does nothing to diminish its potency. This chemical resilience makes the toxin one of the most feared natural compounds in seafood safety. Regulatory authorities in many countries ban the sale of wild puffer altogether, and international guidelines classify the fish among the most hazardous marine species for consumption. One of the most striking scientific aspects of tetrodotoxin is that it does not spread uniformly throughout all pufferfish individuals. Different species contain different concentrations, and within a single species, levels vary depending on diet and environmental factors. Juveniles may carry less toxin than adults, and seasonal changes may influence toxicity levels in certain organs. This variability contributes to the unpredictability of poisoning, making traditional knowledge insufficient without scientific precision. Licensed chefs undergo rigorous state examinations, not only in cutting technique, but in species identification, toxin distribution, and the legal protocols surrounding disposal of toxic tissues. Every scrap of discarded organ tissue must be handled as hazardous waste, secured in containers that prevent scavengers or untrained individuals from accessing them. The pufferfish's place in marine culture and ecology therefore sits at a unique intersection of fascination and danger. It embodies the idea that not all threats in nature present themselves with aggression, and not all beautiful or gentle-appearing animals are safe to touch, let alone consume. The puffer's chemical defense strategy evolved to deter ocean predators, yet humans have repeatedly tested its boundaries by transforming it into high-risk cuisine or casual curiosity. The lessons learned have been costly, marked by medical emergencies, cultural reverence, and an ever-deepening appreciation for the complexity of marine toxins. As the tide rises and the seagrass meadow sinks beneath the shifting water, a small puffer drifts once more between green curtains of swaying blades. It rotates slightly, inspecting the world with patient eyes that express neither fear nor threat. It carries no malice, no intent to harm. Its danger exists only because evolution dictated that a slow, soft-bodied fish needed extraordinary defenses to survive among faster predators. Admiring such a creature from distance honors that evolutionary bargain. Touching it, chasing it, or attempting to prepare it without expertise violates it entirely. In the end, the pufferfish remains a reminder that the ocean's most hazardous secrets are often hidden within its most innocent forms. The small, rounded fish that floats like a drifting ornament is, in truth, one of the sea's most sophisticated chemical engineers. And while its inflation may look comedic and its eyes may appear gentle, its body carries a toxin capable of shutting down the most essential human reflex, the simple, continuous act of breathing. The shoreline looks harmless at first glance. Pale sand, warm shallows, and a light chop rolling in from a distant reef. Morning sun reaches across the surface with a soft golden tilt, catching flecks of suspended plankton and scattering them like drifting dust in a cathedral of water. On the surface, the sea feels familiar and predictable, a place built for play rather than caution. Yet beneath this shallow brightness lies one of the most efficient biological weapons ever engineered by evolution, and it moves with a silence that borders on deceptive artistry. The box jellyfish is not the dramatic monster that many expect from a venomous marine predator. Its bell is pale and nearly invisible. Its tentacles trail like threads of spun glass. But it occupies a coastline that countless travelers enter without even a second thought. And that is precisely how it thrives. Box jellies inhabit tropical and subtropical waters across the Indo-Pacific, drifting through bays, river mouths, mangrove channels, and calm beaches that appear entirely benign. In many regions they arrive seasonally, congregating when winds shift and currents push warm, nutrient-rich water toward land. Shallow water does not deter them. In many cases, it is exactly where they prefer to hunt. The slight warmth of the sunlit zone accelerates their metabolism, and the density of small fish and crustaceans along the shoreline makes it a reliable hunting corridor. From above, nothing reveals their presence. The bell refracts sunlight so efficiently that it all but disappears in the moving shimmer of the shallows. The tentacles can stretch several meters when fully extended, yet they remain thin enough for light to pass through unobstructed. A swimmer can glide directly into a curtain of tentacles without ever noticing the shift in texture or temperature. What makes this creature an outlier among jellyfish is not merely its transparency or its proximity to humans, but its active hunting ability. While many jellyfish drift passively with currents, the box jellyfish possesses a simple but effective form of vision. using clusters of light-sensitive cells arranged in structures called rhopalia. These allow the animal to detect contrast, navigate obstacles, and orient itself toward productive feeding grounds. The bell contracts rhythmically, pushing it forward with deliberate pulses. In calm water, these movements are easy to miss, yet they enable the animal to occupy specific pockets along the beach where upwellings, shoreline geometry, and small fish congregations align. The beachgoer perceives only clear water. The box jellyfish perceives opportunity. When a tentacle touches skin, the event is instantaneous. Nematocysts, microscopic stinging capsules packed by the millions along each tentacle, fire in less than the time it takes for a camera shutter to blink. They do not merely prick. They launch harpoon-like tubules tipped with spine-like barbs, delivering venom directly into the victim's tissue with mechanical force and chemical precision. The venom is a cocktail evolved to subdue fast-moving prey, and humans with much larger cardiovascular systems become collateral casualties of its potency. The first sensation is a burning so sharp and overwhelming that the signal floods the nervous system before the brain fully registers what has happened. Victims describe it as if lines of fire were being dragged across their skin, or as if boiling metal were being pressed into the flesh. These metaphors barely approximate the physiological reality. The venom attacks nerve endings, disrupting ion channels and forcing an onslaught of uncontrolled electrical activity that radiates through sensory pathways. Entire arcs of tentacles can adhere in seconds, drawn tight by the slightest movement. Each additional brush adds thousands more nematocysts to the assault. The venom then spreads deeper, reaching the cardiovascular system. In severe stings, the heart struggles almost immediately. The venom forces the heart cells to contract uncontrollably, as though each fiber has been individually hijacked. Arrhythmia can occur within minutes. If enough venom is delivered, cardiac arrest can follow so swiftly that victims collapse before reaching the shore. Some never make it out of the water at all. This is why box jellyfish incidents, though relatively rare compared to the number of swimmers entering these beaches each year, carry such a high severity rate. The creature does not need to be large. It only needs a few tentacle lengths to deliver a dose that overwhelms a human body. Real cases underline the stakes with brutal clarity. In northern Australia, several fatal encounters have occurred within sight of lifeguard towers. Children have run into knee-deep water, brushed a tentacle, and collapsed almost immediately. In parts of Southeast Asia, fishermen wading through estuaries have been caught off guard by drifting jellies that rode the incoming tide. Some suffered cardiac arrest before help could be summoned. Survivors often describe a burn pattern etched across their bodies like branching lightning scars, a visible map of where the tentacles contacted their skin. These welts can persist for weeks. The internal effects, however, can last far longer, including lingering pain, muscle weakness, and disturbed heart rhythm. Emergency response is a race against biological chemistry. Vinegar, though simple and almost unimpressive as a tool, is one of the few immediate defenses available on the beach. It does not neutralize the venom, but it halts the continued firing of nematocysts that have not yet discharged. This buys crucial seconds. The stinging capsules that have already fired cannot be undone, but preventing additional ones from activating can reduce the venom load dramatically. Removing tentacles must be done with extreme care, ideally using gloved hands or a barrier material, because pressure and rubbing can cause remaining nematocysts to release. From there, efforts shift to stabilizing the victim's airway, breathing, and circulation. In severe cases, resuscitation begins before the person even leaves the sand. The difference between survival and loss often comes down to whether trained responders are nearby and whether the initial venom dose was large enough to destabilize the heart. For many tourists, however, the risk feels abstract until the moment it becomes real. The typical beach visitor associates danger with sharks or rip currents, dramatic threats that match cinematic expectations. A soft, clear jelly, drifting like a ghost in shallow water, seems closer to a harmless floating ornament than a predator. This miscalculation is partly rooted in appearance. The box jellyfish lacks visual cues of danger. It has no teeth, no claws, no aggressive posture. It hangs beneath the surface like a misplaced fragment of air. The tiny contractions of its bell are almost charming. the opposite of a creature associated with lethal encounters. But nature often hides its most effective weapons behind a facade of simplicity. The box jellyfish does not need intimidation. It relies on invisibility. Even after incidents are reported, visitors often underestimate how such a creature behaves. They imagine it stationed in deep water or drifting far offshore. They assume they will see it, or they believe that stings result from carelessness. In reality, box jellies frequent the same sheltered spots that swimmers prefer. Warm shallows, sandy bottoms, estuarine channels, and bays protected from waves are ideal for both families and jellyfish. They do not seek conflict. They simply follow the ecological logic that places small fish near shorelines, and where prey gathers, predators gather too. The tentacles themselves demonstrate another layer of biological specialization that many fail to recognize. They can shorten or lengthen depending on the jellyfish's needs. When hunting, the tentacles stretch outward, creating a barely perceptible net that intercepts anything moving through the water. When disturbed, the jelly may contract them to reduce drag and retreat downward. This ability to alter shape and spread in response to subtle cues helps explain why swimmers can suddenly encounter multiple trailing filaments without ever seeing the bell. The tentacles themselves, twined by sheer accident around an arm or leg, can deliver enough venom in those first milliseconds to define the entire outcome of the event. The ecological role of the box jellyfish complicates any simplistic view of it as merely a hazard. It is a predator that keeps small fish populations in check, and its seasonal movements often mirror the migration of juvenile fish that cluster in protected bays. Without predators like these jellies, local ecosystems could shift in unstable ways, allowing certain species to explode in number, while others decline. The danger it poses to humans is an unintended intersection of evolutionary design and human recreation patterns. The jellyfish's weaponry evolved for quick kills on creatures much smaller than humans, yet the mechanism does not differentiate. It activates upon contact, following a script written through millions of years of predation. Tourist behavior often widens the gap between perceived and actual risk. People associate clear water with safety, ignoring the fact that transparency enhances the jelly's camouflage. Children splash noisily, creating water disturbances that tug tentacles toward them. Adults wade far from shore under the illusion that shallow water offers refuge. Some beaches install nets or announce seasonal warnings, yet curiosity frequently overrides caution. The truth is that box jellies turn the shoreline itself into a zone where risk begins earlier than expected. The first few meters of water can be the most dangerous, not because predators are lurking with intention, but because invisibility removes the very cues humans rely on to detect danger. The challenge, then, is learning to coexist with an organism that neither chases humans nor avoids them. Understanding its behavior transforms the shoreline from an assumed playground into a more honest ecological intersection. The sea is full of predators that display their power openly. Sharks with their unmistakable silhouettes, crocodiles with their armored heads breaking the surface, barracudas with their silver torpedo shape flashing under the sun. The box jellyfish is the opposite. Its threat is quiet, immediate, and tied to biology rather than aggression. Its danger lies in the fact that the beach itself can bite first, long before any swimmer sees the weapon that struck them. In this fragile balance between beauty and peril, the box jellyfish serves as a reminder that nature does not arrange itself around human expectations. The shoreline is not a barrier between safety and wilderness. It is a merging point where countless species, each following their own evolutionary trajectory, converge in the same warm shallows. And among them drifts a predator so refined in its simplicity that most never notice it, until the sea itself seems to ignite on their skin. The shallow reef flat looks peaceful in the late afternoon, when the tide drops low enough to expose patches of pale sand between scattered coral rubble and tide pools. The water settles into a soft, glass-like stillness, broken only by the sound of distant waves hitting the outer reef crest. Sunlight slips through the surface in wide ribbons, illuminating the sandy bottom with a warm, deceptive calm that encourages beachgoers to wade out and explore. It is the kind of scene that invites bare feet, unhurried steps, and the comfort of assuming that anything dangerous would be obvious long before it could cause harm. Yet beneath this calm, camouflaged so thoroughly that the eye passes over it again and again, lies a predator whose greatest weapon is not movement or aggression, but stillness. The stonefish, perfectly disguised as a lumpy rock or a piece of broken coral, waits without intention, without malice, and without warning. In the places where swimmers and snorkelers prefer to stand and adjust their masks, this fish positions itself with evolutionary precision. A stonefish does not hunt with speed, and it does not need to. Its existence is rooted in ambush. Its body is a collection of rough textures, mottled colors, wart-like nodules, and irregular shapes that mimic the broken fragments of the reef floor. When it buries itself slightly in the sand, only the faint outline of a mouth and two tiny passive eyes interrupt the illusion. Even trained marine biologists sometimes struggle to detect them until they are directly pointed out. The fish's camouflage is not simply good, it is one of the most effective visual deceptions in the natural world, evolved over millions of years of avoiding detection by both predators and prey. This invisibility is a survival strategy for the fish, but it becomes a catastrophic failure point for humans who assume that the rocky shapes under their feet are lifeless. Stonefish prefer shallow zones because these regions provide dense cover and abundant small fish that graze along the sand. But the same habitat is also where people naturally pause. Wading swimmers hover in these areas because the depth feels manageable and the ground feels stable. Children often crouch here, reaching for shells. Tourists adjust snorkel straps. Kayakers step out to stretch their legs on submerged sandbars. And local fishers, familiar though they may be with the animals, still encounter them unexpectedly along the intertidal zone. The fish does not flee when approached. Flight is rarely part of its behavioral toolkit. Instead, it relies on stillness, trusting that its visual disguise will remain unbroken. This means an unsuspecting foot can descend directly onto it, triggering one of the most notorious venom delivery systems in the marine world. Across the stonefish's back lies a row of stout dorsal spines that resemble broken coral stubs. These spines remain harmless until downward pressure activates them. The fish does not need to aim or strike. A foot landing on its back forces the spines to rise through the skin, pushing venom sacs against one another and launching a dose of potent neurotoxin directly into the tissue of whatever pressed down. In that instant, the fish becomes a passive but devastating weapon. The venom is not injected by aggression, but by mechanical design. A defensive adaptation meant to deter predators such as sharks, rays, or larger fish that might attempt to swallow it. The venom is an exceptionally complex blend of proteins designed to inflict immediate, overwhelming pain. The initial sensation is sharp, almost electric, as if the nervous system were being struck with a sudden surge of uncontrolled current. Victims often describe the pain as radiating outward in waves, intensifying with each passing second, transforming from a localized sting into a full limb agony that feels deep and crushing. Some compare it to bones being shattered. Others describe it as a burning that spreads faster than their breath can match. These descriptions may sound exaggerated until one considers the venom's true purpose. In the wild, the goal of the stonefish's defense is to guarantee that any predator, regardless of size or ferocity, learns immediately and decisively that attempting to consume this fish will result in absolute misery. Once inside the human body, the venom begins to attack tissues and disrupt cellular function. In severe cases, it can cause necrosis, areas of flesh that begin to die as circulation collapses. Swelling can become extreme, turning an entire foot or leg rigid. If stung on the hand, victims often lose mobility for days, and in some cases, nerve damage can linger for weeks or months. The venom also affects the cardiovascular system, inducing rapid heart rate, sweating, and nausea. Some individuals experience a drop in blood pressure that leads to dizziness or collapse. These physiological responses reflect the venom's ability to disrupt ion channels, which are essential for nerve conduction and muscle contraction. When these channels malfunction, pain signals amplify to unbearable levels, while muscle fibers misfire or cease responding altogether. The most severe outcomes occur when multiple spines penetrate deep into the body, delivering a high dose of venom. Historically, there have been cases throughout the Indo-Pacific where victims suffered life-threatening complications after stepping on stonefish concealed in shallow tide zones. Without prompt medical care and antivenom, the combination of tissue destruction and systemic shock can become overwhelming. Fortunately, fatalities are rare when proper treatment is available. The challenge lies in recognizing the danger for what it is before symptoms escalate. A sting often triggers immediate panic, not only because of the extreme pain, but because victims rarely realize what happened in the moment of contact. Many assume they stepped on a piece of broken coral or sharp rock until the agony escalates far beyond what such an injury could cause. The shock of realizing that something hidden beneath the sand delivered the injury often compounds the distress. Tourists in particular struggle to identify the source because they do not expect danger in water shallow enough to wade through casually. Emergency treatment involves immersing the affected limb in hot water, as heat can help denature some components of the venom. The water must be hot enough to be uncomfortable but not scalding, a delicate balance for someone already in profound pain. This method does not negate the venom entirely, but it offers significant relief by reducing the activity of the toxic proteins. Severe cases require antivenom, administered in clinical settings. Antivenom can halt the progression of tissue damage and reduce systemic symptoms, but it must be given promptly to prevent lasting harm. Yet the most effective protection begins long before any medical intervention. Simple behavioral precautions drastically reduce the likelihood of stepping on a stonefish. Wearing protective footwear creates a barrier strong enough to prevent spines from penetrating deeply. Even reef-safe boots made of thick neoprene can make the difference between a minor injury and a severe envenomation. For those wading in sandy or rubble-strewn areas, shuffling the feet instead of lifting them reduces the chance of stepping down hard on a concealed fish. The motion pushes sand ahead, disturbing anything hidden at the surface. A stonefish, feeling the shifting sediment, may shift slightly or reveal itself through movement, although it still usually remains camouflaged. It is not a guarantee, but it is a layer of safety that buys crucial seconds. Another rule is equally important: never pick up random rocks underwater. The temptation to examine a shell, coral fragment, or interesting stone is strong, especially in clear, shallow water where everything looks harmless. But stonefish often resemble these exact objects. Their skin textures include spines, bumps, and ridges that mimic algae-covered rubble. Their colors match the tan, brown, and gray shades of the reef floor. What appears to be a small, harmless rock with a mossy coating may twitch in one direction the moment it is disturbed, often too late for the handler to react before spines press into the palm. The symbiotic relationship between stonefish and their habitat reinforces the idea that danger in nature frequently comes from organisms that attempt to avoid conflict rather than seek it. Stonefish do not chase prey through the reef. Instead, they wait with unbroken patience, conserving energy and relying on prey to make the mistake of passing within striking distance. When a small fish swims close enough, the stonefish opens its mouth with astonishing speed, creating a suction force that draws the prey inward in a fraction of a second. The strike is so fast that high-speed cameras are required to capture its full motion. This ambush strategy minimizes movement and allows the fish to maintain its camouflage indefinitely. The same invisibility that serves the stonefish so well in hunting also makes it one of the most common causes of venomous marine injury. Humans, with their tendency to trust visual cues, fail to acknowledge the biological arms race that shaped many reef organisms into masters of deception. In the stonefish's world, looking like a piece of rubble is an evolutionary advantage. In the human world, it is a hazard that hides in plain sight. Understanding this duality transforms the shallow water environment from a playground into an ecological intersection where survival strategies clash with human behavior. The stonefish is not a villain. It is a species perfectly adapted to a habitat that humans increasingly enter without appreciating the rules that govern its inhabitants. It survives by blending into the reef floor and discouraging predators with a venom system unmatched in intensity. The danger arises not from aggression, but from the unpredictable overlap between human feet and a creature designed to remain unseen. As the tide rises again and the colors of the reef flatten into late-day shadows, the stonefish remains exactly where it has been for hours, unmoving, unnoticed, and unintentional in its threat. Nature's most dangerous encounters often occur not in deep water or dramatic open ocean scenes, but in the quiet, ankle-deep shallows, where the line between safety and risk disappears beneath a thin sheet of clear water. Here, evolution has crafted a creature that punishes carelessness, rewards caution, and turns every unexamined rock into a reminder that the ocean does not adjust itself for human comfort. In the blue shallows where the reef drops gently toward deeper water, a shape begins to weave through the drifting curtains of sunlight like a loose ribbon carried by a slow current. At first glance, it looks like a length of discarded rope, shifting lazily with each passing wave. Only when it changes direction with quiet intention does its identity sharpen. A sea snake, slender and patterned with pale bands, rises through the water column with a calmness that feels almost rehearsed. Its movement is fluid, but not hurried, the body curving in wide, deliberate strokes, powered by a paddle-like tail designed for swimming rather than anchoring to land. There is no sudden darting or aggressive posture, only a curious, drifting presence that seems to watch everything and worry about nothing. This is precisely why divers often underestimate these animals. Their serenity disarms the human mind long before the reality of their biology is understood. Sea snakes occupy a unique evolutionary space. They are fully marine reptiles, breathing air, but spending the majority of their lives beneath the surface. Many species forage along coral rubble or sandy channels for eels and small fish, slipping into crevices with bodies more flexible than nearly any terrestrial snake. Their lungs extend almost the full length of the body, acting as buoyancy regulators that allow them to hover in mid-water with minimal effort. Through specialized scales and physiological adaptations, they can remain submerged for extended periods, exchanging small amounts of oxygen across their skin while conserving muscular energy. These snakes evolved not for speed, but for efficient gliding, and their unhurried motions make them appear indifferent to the world around them. This relaxed demeanor is often mistaken for approachability. Divers frequently describe encounters with sea snakes as surprisingly intimate. Unlike many marine predators that flee from bubbles or flashes of light, sea snakes often swim toward humans with genuine curiosity. They approach slowly, tasting chemical cues with their forked tongues, inspecting each newcomer as though evaluating an unusual object on their reef. Sometimes they spiral upward alongside a diver's fin or hover beside a mask, staring with unblinking eyes. This behavior is not aggression. Sea snakes rely heavily on chemical and tactile exploration. In the absence of fear, they simply investigate. But curiosity in a venomous reptile carries inherent risk, especially for those unfamiliar with its body language or unaware of the potency hidden behind its calm exterior. The venom of sea snakes is among the most powerful in the natural world. It evolved for subduing fast, slippery prey in the confined environment of reef crevices, where a strike must immobilize instantly to prevent escape. The toxin interferes with neuromuscular function, disrupting the communication between nerves and muscles. Early symptoms of envenomation include stiffness in the jaw, a feeling of heaviness in the limbs, and progressive muscle weakness. Within hours, paralysis can spread to respiratory muscles, leading to respiratory failure if not treated. Despite the severity of the venom, sea snake bites are relatively rare for humans, largely because the snakes do not view people as prey. When bites do occur, they often result from humans accidentally grabbing or blocking the snake's movement, forcing the animal into defensive action. Many sea snakes have small fangs positioned toward the front of the mouth, and their bite mechanics are adapted for thin-skinned prey such as fish. Humans are not part of their evolutionary reference frame. Most defensive bites deliver less venom than predatory ones, and some may even be dry bites, where no venom is injected. But relying on the chance of a dry bite is reckless, because when venom is delivered, the dose can be potent enough to overwhelm large mammals rapidly. While fatalities are uncommon when medical care is available, they have occurred in remote coastal regions and among fishers who inadvertently trap snakes in nets and attempt to remove them with bare hands. The danger of sea snakes is therefore not rooted in their behavior, but in human misinterpretation of that behavior. Their calmness leads divers to believe the animals are tame. Their delicate movements make them seem fragile. Their unthreatening appearance encourages proximity. But the potential for rapid escalation exists whenever a diver reaches out, blocks a snake's path, or attempts to lift it for photographs. These interactions transform a peaceful encounter into a hazardous one. A sea snake that feels trapped may thrash or twist in an attempt to escape, and in close quarters this movement can bring fangs within striking distance. Understanding sea snake ecology provides deeper insight into their temperament. Unlike terrestrial snakes that rely on basking to regulate body temperature, sea snakes use warm, shallow water and solar-heated surfaces to maintain metabolic stability. Some species come to the surface to breathe and rest, lying motionless except for brief lung expansions before diving again. Others swim inland during certain tides to forage across seagrass meadows. Their oxygen demands require periodic surfacing, yet they remain vulnerable to predators such as sharks and large fish during these moments. For that reason, they evolved a strategy centered on calm persistence rather than frantic escape. When confronted by potential threats, they remain composed, conserving energy rather than fleeing in bursts that could leave them gasping for air too far from the surface. Their reproductive cycles also reveal the trade-offs unique to a marine lifestyle. Most sea snakes give birth to live young, allowing them to spend their entire lives at sea without returning to land. This adaptation requires careful internal thermoregulation, achieved partly through basking near the surface and partly through physiological mechanisms that balance heat distribution within the mother's body. When carrying developing embryos, females are especially docile, avoiding unnecessary movement to conserve oxygen and energy. Divers who unknowingly approach a pregnant female may observe her drifting slowly, seemingly apathetic. Yet even in this vulnerable state, she carries venom potent enough to immobilize prey several times her mass. Curiosity plays a crucial role in sea snake survival. They must inspect potential hiding spaces, evaluate scent trails, and examine objects that do not match familiar environmental cues. Humans are an anomaly in their world. Large, bubble-producing, brightly colored shapes that lack clear meaning. To a sea snake, approaching a diver is a method of identification, not confrontation. When the snake gently presses its snout against a diver's fins or wetsuit, it is gathering chemical information through specialized sensory receptors. This behavior can be startling for those unprepared, but it is not a prelude to aggression. Problems arise when humans misread this examination. Divers who panic or flail may inadvertently block the snake's retreat. Others, emboldened by the snake's gentle behavior, attempt to touch or guide it away, forgetting that handling any wild animal compresses its space and eliminates its escape routes. Sea snakes rely on open water to avoid threats. When this space disappears, the reptile must defend itself, and its only effective defense is venom. There is an additional hazard that even experienced divers sometimes overlook: the speed at which a sea snake can strike when startled. Although their normal swimming is leisurely, their strike is fast, precise, and capable of reaching surprising distances due to the flexibility of their elongated bodies. A snake coiled briefly beneath a coral ledge or tangled unintentionally in diving equipment may respond with a defensive bite before the diver even perceives danger. This is why guides and marine biologists emphasize distance rather than familiarity as the foundation of safe encounters. The symptoms of envenomation unfold gradually but inexorably. After the initial bite, which is often painless, muscle stiffness becomes noticeable, followed by weakness, especially in the legs. Victims may feel as if they are wading through heavy sand, unable to muster strength. Without treatment, the toxin spreads through the bloodstream, reaching the diaphragm and intercostal muscles that facilitate breathing. Respiratory compromise follows. The mind remains alert, witnessing the gradual shutdown of muscular control, a hallmark of neurotoxic paralysis. It is a progression that underscores the seriousness of any sea snake bite, regardless of the circumstances in which it occurs. Despite their venom, sea snakes remain among the most peaceful animals encountered by divers. Their ecological role contributes significantly to reef stability by managing populations of benthic fish and eels. Some species specialize in hunting within crevices, inserting their narrow heads deep into holes to flush prey outward. This behavior requires exceptional agility and exposes them to predators if performed too openly, reinforcing their reliance on camouflage, stealth, and avoidance rather than confrontation. Humans are not a part of their evolutionary pressures. They have no reason to fear us, and no instinct to attack without provocation. This dynamic creates a simple rule that governs all safe interactions: hands off. When divers remain passive, sea snakes wander freely, often investigating and then drifting away with the same unhurried motion. When humans keep respectful distance, the encounter becomes a rare opportunity to observe a reptile perfectly adapted to life in the sea. The relationship succeeds only when humans resist the temptation to treat the snake as approachable or safe to touch. Admiration from afar maintains harmony. Contact breaks it immediately. In many ways, sea snakes capture the broader lesson of marine life. That danger is not always loud, aggressive, or visually intimidating. Sometimes it arrives wrapped in gentle movement, curious eyes, and a body that looks more like a discarded rope than a predator. Their beauty lies not in dramatic display, but in subtlety. The quiet glide through dappled light, the effortless weaving across reef contours, the delicate inspection of unfamiliar shapes. This grace coexists with one of the most potent venoms on the planet, a combination that demands humility from those who enter their world. As the snake descends toward the reef once more, disappearing into the shifting geometry of coral shadows, it leaves behind no trail of disturbance, no sign of threat. It is neither friend nor foe, only a creature shaped by its environment, capable of peaceful coexistence when treated with respect. The ocean does not operate by human assumptions. It rewards caution, patience, and awareness. And when a rope-like form rises from the depths with unhurried curiosity, the wisest response is simply to allow it space to continue its ancient, elegant journey. In the quiet band of water where the shoreline meets the rocky shallows, the sea reveals one of its most deceptively hazardous inhabitants, creatures that neither swim nor chase, but simply exist in stillness, waiting for a careless footstep to turn an ordinary afternoon into weeks of pain. The sea urchin does not advertise its presence with motion. It clings to the undersides of stones, wedges itself between crevices, and forms dark clusters along reef plates, where waves break with rhythmic certainty. From above, these shapes appear harmless, almost decorative, like small starbursts or dark pincushions arranged across the sea floor. Yet beneath this stationary form lies a suite of defensive adaptations that evolved long before humans began sliding across their habitat in bare feet. To understand the sea urchin is to recognize that danger in the ocean is often passive, waiting not by intention, but by proximity. The surface of a sea urchin is covered in spines, each one connected to a small joint that allows subtle movement. These spines serve two primary functions: protection from predators and assistance with locomotion. They are not uniform. Some species carry long needle-like spines fragile enough to snap with light pressure. Others feature thick, clubbed spines designed to deter fish and octopuses. The most hazardous spines, however, fall somewhere in between, thin enough to penetrate skin, brittle enough to break inside it, and chemically structured in ways that ensure they begin dissolving slowly once embedded. An encounter with such spines rarely ends at the moment of impact. Instead, it begins a sequence of physiological responses that can linger for days or even weeks. Stepping on a sea urchin typically occurs in the same environment: rocky shores where waves recede just enough to reveal small pools and uneven footing. These areas draw swimmers, snorkelers, and tide pool explorers who believe shallow water equates to safety. The human eye, accustomed to scanning for movement as a primary warning sign, often overlooks the dark, unmoving silhouettes clinging to rock surfaces. The foot descends, pressure aligns with a cluster of slender spines, and the result is immediate: a series of sharp punctures, each one delivering a brittle fragment deep into soft tissue. The pain is instantaneous, but rarely explosive. Instead, it blooms outward gradually, a spreading ache accompanied by the disconcerting knowledge that multiple foreign objects now reside within the foot. What makes these injuries particularly troublesome is the structure of the spines themselves. Composed largely of calcium carbonate in a porous, crystalline form, they fracture under stress and crumble into smaller pieces. These fragments wedge themselves between muscle fibers, tendons, and connective tissue. Because the spines are fragile, attempts to remove them manually often push them deeper. Over time, the body responds with inflammation, swelling, and tissue irritation. In many cases, the fragments dissolve slowly, leaving behind discoloration and localized soreness that may persist long after the initial wound closes. Some individuals develop granulomas, small, hardened nodules formed when the immune system encapsulates particles it cannot break down. These granulomas can remain for months, each one a tiny archive of an encounter that lasted only a moment. More severe complications arise when spines lodge near joints or tendons. In these areas, even small movements cause microabrasions as the fragment shifts within the tissue, triggering extended pain and limited mobility. When embedded near a toe joint, the discomfort can disrupt walking. When lodged near the heel, inflammation may radiate upward toward the ankle. If spines penetrate deeply enough, they may introduce bacteria from the surrounding marine environment into the tissue, setting the stage for secondary infections that produce heat, swelling, and persistent tenderness. In rare instances, untreated infections can spread, creating long-term medical concerns that require clinical intervention. The ocean itself has played a role in shaping the defensive strategy of sea urchins. Predators such as triggerfish, wrasses, and sea otters have evolved specialized techniques to overcome the armor of an urchin, whether by flipping the animal over to expose its vulnerable underside, or by breaking spines deliberately to access the soft internal tissues. This predator pressure has selected for spines that are both sharp and brittle, sharp enough to deter attackers, brittle enough to discourage persistent handling. In other words, the same mechanical traits that evolved to protect urchins from natural predators now guard them against human contact. Human interactions with sea urchins tend to fall into two categories: accidental and avoidable. The accidental encounters happen when swimmers paddle through rocky shallows, unaware that their feet hover only centimeters above clusters of spines. The avoidable encounters happen when people, drawn in by curiosity, pick up urchins to examine them, or attempt to clear a patch of rock for sitting or walking. In both cases, the result is the same: spines embedded where they do not belong, followed by a gradual spread of discomfort that signals the beginning of a tedious recovery process. Unlike some marine injuries that deliver immediate systemic symptoms, sea urchin wounds are localized and deceptively mild at first. The danger lies not in venom, although a few species do possess mild toxins, but in the mechanical and infectious complications that follow. Understanding the distribution of sea urchins within coastal environments offers clues for avoidance. They thrive in habitats with stable surfaces and plentiful algae. Rocky foreshores, coral rubble zones, and the shadowed undersides of boulders create ideal anchoring points. These areas also attract humans for similar reasons: stability, shelter from waves, and interesting wildlife. Unfortunately, where humans find footing, sea urchins often find home. Their dark colors allow them to blend seamlessly into rock crevices, especially when shadows obscure their outlines. Even experienced divers sometimes place their hands against a rock wall to stabilize themselves, only to recoil as spines enter the palm or fingertips. Movement technique becomes essential in preventing contact. In sandy shallows, shuffling the feet helps alert stingrays, but in rocky shallows, lifting the feet slowly and placing them with intention reduces the risk of stepping directly onto an urchin. Protective footwear serves as another line of defense. Thick-soled booties can prevent spines from penetrating fully, absorbing the impact and distributing pressure over a broader area. Gloves are equally critical for those exploring tide pools or navigating rocky entries. A single misjudged handhold can result in multiple punctures across the palm, a particularly problematic injury since hand spines interfere with daily tasks far more than foot injuries. The importance of these precautions becomes clear when considering the long healing timeline of untreated spine injuries. Once embedded, fragments can migrate subtly through surrounding tissue, propelled by muscle movement and pressure from walking or swimming. Their dissolution rate varies depending on spine composition and individual physiology. Some spines dissolve within days, others persist for weeks. During this period, inflammation can flare repeatedly, especially if the tissue is stressed. Should bacteria introduced at the moment of puncture begin to multiply, pain may increase and swelling may spread. In these cases, medical evaluation becomes necessary. Radiographs rarely detect spine fragments due to their composition, but experienced clinicians recognize the characteristic pattern of punctures and subsequent tissue reactions. The body's attempt to resolve the foreign material offers insight into the complexity of immune response. Phagocytic cells surround the fragments, gradually breaking down portions of the spines and depositing minerals around them. If the fragments are too large or too deeply embedded, the body encapsulates them in fibrous tissue, forming a granuloma. These nodules are not dangerous, but can be sensitive and persistent, especially if they form near joints. In some cases, surgical removal becomes the only solution, though this is reserved for chronic or debilitating cases. Despite their defensive hazards, sea urchins play an essential role in marine ecosystems. They graze on algae that would otherwise overwhelm reef surfaces, ensuring corals receive enough light to survive. Their feeding activity influences the distribution of algae, sponges, and coral recruits, shaping the structure of entire reef communities. Some species even maintain the delicate balance between coral growth and algal competition, preventing reef surfaces from becoming smothered. When urchin populations collapse, whether from disease or overharvesting, algal blooms often follow, illustrating how intertwined the health of an ecosystem can be with the smallest of its inhabitants. For humans entering their environment, awareness becomes the most effective tool. Recognizing the dark, rounded shapes among rocks, understanding that shallow depths do not guarantee safety, and wearing proper protection all reduce risk. The ocean rewards those who move with deliberate caution. It punishes those who assume appearance equals safety. A sea urchin will never chase, never strike, never lunge. Its danger manifests only when another organism intrudes upon its space without noticing its presence. As waves recede once more, pulling sunlight across the uneven stone floor, the silhouettes of urchins remain perfectly still. They cling to their world with no hostility, no intention to harm, only the quiet certainty of creatures adapted to survive through passive defense. In this calm, the lesson becomes clear. The ocean's hazards are not always dramatic or immediate. Sometimes they are small, silent, and waiting beneath a thin layer of clear water, turning a single misplaced step into days or weeks of lingering reminder. In the soft, pale shallows, where waves fold gently over the seafloor, the ocean projects a sense of innocence that misleads even experienced swimmers. Sand ripples in delicate patterns sculpted by the tide. Small fish skate past in flashes of silver, and sunlight spreads across the bottom in warm, shifting grids. It feels like the safest zone in the marine world. No depth, no darkness, no signs of predators. Yet this seemingly tranquil interface between land and sea is precisely where one of the ocean's most misunderstood hazards waits. Not through intention or ambush, but through evolutionary convenience. Buried beneath a thin veil of sand, a stingray rests motionless, its eyes alone betraying the presence of a creature designed for concealment. To an approaching swimmer, there is no warning, only the sensation of stepping onto something that is not quite rock, not quite sand, and then the sudden, devastating reaction that follows. Stingrays use the sandy bottom as both camouflage and refuge. Their flattened bodies and broad pectoral fins give them the shape of a living wing, adapted to glide with minimal energy expenditure. When they settle onto the seafloor, they generate gentle pulses that push sand upward and across their bodies, covering themselves in a fine layer of sediment. In clear water, the only visible features are two small eyes protruding from the sand and the faint outline of spiracles, specialized openings that draw water into the gills even while the animal lies buried. This adaptation allows them to remain hidden for extended periods without suffocating, making them nearly impossible for casual beachgoers to detect. Because they frequent sandy coves and shallow channels, precisely the areas people wade for safety, accidental encounters become inevitable. When disturbed, a stingray does not flee immediately. Its instinct is to lift away from the threat. But when something presses down on its body, such as a human foot, the animal's defensive reflex engages with astonishing speed. The tail, which often extends as long as the ray's body, whips upward in a rapid, arcing motion. At the base, or along the length of this tail, lies the stingray's primary defense. a barbed spine sheathed in a thin layer of venomous tissue. The spine is not used for hunting. Rays feed on mollusks, crustaceans, and small bottom-dwelling fish. Instead, it is a strictly defensive weapon, evolved to discourage predators such as sharks or large bony fish from attacking. For a creature shaped like a flattened disc, the tail spine provides a final option against being bitten or crushed. But against a human leg or foot, this natural weapon becomes a severe medical hazard. The mechanics of a stingray strike illustrate the efficiency of its design. The spine is serrated with dozens of recurved barbs angled backward toward the base. During a strike, the spine pierces flesh with the sharpness of a spear, and the barbs create resistance that prevents easy withdrawal. This backward-facing structure means that any attempt to pull the spine out can cause further tearing of tissue. Along the spine's surface lies a thin layer of integumentary sheath containing venom. When the spine punctures skin, this sheath ruptures, releasing venom into the wound. The venom does not circulate systemically in most cases. Instead, it triggers intense localized pain and inflammation. Victims describe the pain as deep, penetrating, and rapidly intensifying, spreading outward in waves that pulse with the rhythm of the heartbeat. The wound often bleeds heavily, not because of venom, but because of the mechanical damage inflicted by the serrated barb. The tissue damage can be significant even without venom involvement. The spine's jagged structure creates lacerations that expose underlying muscle, tendon, or bone. When the strike hits the foot or ankle, mobility can be compromised for days. When the spine punctures deeper regions, the consequences escalate. One of the most sobering lessons about stingray injury derives from a highly publicized fatality in which a spine punctured the chest cavity of a well-known naturalist. The location of the strike, not the venom, proved fatal, demonstrating that even a species perceived as calm and passive can cause lethal injury under the wrong circumstances. This event reshaped public understanding of stingrays, reminding the world that a gentle marine animal can still deliver a catastrophic wound if startled at close range. The venom itself is a complex mixture of proteins that induce intense pain, swelling, and sometimes tissue necrosis. It is not among the most potent marine toxins, but combined with mechanical trauma, it creates a potent threat. Initial symptoms include throbbing pain, rapid swelling, and increased sensitivity around the wound. In some cases, muscle cramping follows, caused by the toxin's interaction with nerve endings and local musculature. If untreated, the wound can become infected due to bacteria introduced from the spine or from sand forced into the tissue during impact. Marine environments contain species of bacteria capable of thriving in wounds, particularly when debris remains within the injury. Because stingray spines often break upon striking hard objects, fragments can remain lodged inside, complicating healing and increasing infection risk. From an ecological perspective, stingrays fulfill essential roles in coastal ecosystems. Their feeding behavior, rooting through sand with powerful undulating motions, helps aerate the seafloor and redistribute sediments. This activity uncovers buried organisms and creates feeding opportunities for other species. Rays also regulate populations of benthic invertebrates, shaping the structure of shallow water communities. Their camouflage, so effective for avoiding predators, also protects them from expending unnecessary energy fleeing creatures that pose no real threat. Unfortunately, this same adaptation increases the likelihood of accidental human contact. The human instinct to move confidently through shallow water contributes to the problem. Waders often step firmly, unaware that a ray could be concealed beneath a thin layer of sediment. The stingray shuffle, a technique taught in coastal regions where rays are common, reduces risk significantly. By sliding the feet through sand instead of lifting them, swimmers alert rays to their presence through vibrations rather than pressure. A ray that senses gradual disturbance is far more likely to glide away quietly than to strike. This behavioral adjustment demonstrates how simple changes in human movement can prevent harmful interactions. Protective equipment further reduces risk. Sturdy water shoes can mitigate shallow strikes by dispersing pressure and preventing deep penetration, although they are not effective against larger rays or full-force strikes. Gloves are essential for divers or fishers who handle nets or interact with rocky structures where rays may rest. The greatest danger occurs when individuals attempt to lift or block a stingray, believing it to be harmless because it appears calm. The ray's composure is not submission, it is energy conservation. Its reflex strike remains ready, triggered not by aggression, but by startle. Understanding stingray behavior provides insight into their defensive instincts. They are not territorial and do not attack proactively. Their sensory adaptations allow them to detect electromagnetic fields, pressure changes, and subtle vibrations, helping them avoid threats long before direct contact occurs. When a large animal approaches slowly, they glide away. When approached quickly or stepped on, they defend themselves with the only tool capable of deterring a powerful predator. In many ways, humans moving through the shallows replicate the behavior of large animals attempting to pin a ray to the bottom. The ray reacts accordingly. In deeper water, rays exhibit striking elegance. They rise from the sand in slow spirals, fins undulating like wings. Their coloration blends soft browns, grays, and muted blues, designed not for visual intimidation, but for invisibility. Their eyes watch from above, while their mouths forage below, creating a sensory world in which danger is interpreted through the sand more than through sight. Their role as bottom dwellers places them at constant risk of being disturbed, and their tail spine evolved as a precise answer to this ecological challenge. As the tide pushes inward and the shallows deepen once more, rays reposition themselves along the sandy terraces, waiting for feeding opportunities delivered by the shifting water. Their presence is quiet, passive, and essential to the ecosystem. They do not require fear, but respect, a recognition that even gentle animals carry defenses shaped by millions of years of survival. A casual wader sees only an empty stretch of water. A stingray sees an approaching weight that could crush it if not avoided. The calmness of these creatures lulls many into a false sense of safety, but the ocean's rules remain unchanged. Threats often lie in stillness, not in pursuit. A buried ray is neither aggressive nor malicious, yet its reflex can change the course of a day, or in rare cases, a life. The lesson is as simple as it is enduring. Move cautiously, watch the sand, and remember that the most dangerous tale in the shallows belongs not to a predator seeking prey, but to a peaceful animal armed only with the instinct to survive. Dawn light spills over the open ocean in slow gradients of silver, tinting the swells with the first hints of warmth as the night retreats below the horizon. Out here, far beyond the breaking surf, but close enough for reefs to imprint the seafloor with rising buttresses of coral, a large shadow glides just beneath the surface. It moves with a composure that suggests the water itself is carrying it, rather than the rhythmic motion of its tail. This is the realm of the tiger shark, a predator whose interactions with the world are defined not only by aggression or hunger, but by curiosity, an evolutionary habit that has shaped countless encounters between shark and human. Its silhouette is unmistakable: broad head, powerful body, and subtle vertical stripes that give the species its name. But it is the behavior, rather than the appearance, that sets the tiger shark apart. Unlike many ocean predators that rely on caution, this shark investigates the unfamiliar. And in the marine world, investigation often begins with a bite. Tiger sharks patrol transition zones where ecosystems overlap: reef drop-offs, surf breaks, deep sandy channels, and the borders between open water and coastal shallows. These areas funnel prey into predictable paths. Sea turtles pass through on migration routes. Injured fish drift on tidal currents. Seabirds fall from the sky after exhausting flights. Every shift in water motion carries chemical signals, vibrations, and scent trails. Tiger sharks interpret this sensory map with extraordinary precision. Their snouts contain electroreceptors capable of detecting the faint electrical pulses generated by muscle contraction. Their eyes, adapted for low light, distinguish contrast even in murky conditions. Their ears detect low-frequency vibrations across impressive distances, but their most distinctive investigative tool is their mouth. Evolution granted tiger sharks serrated, coxcomb-shaped teeth arranged in angled rows along a jaw that exerts impressive force. These teeth are not designed merely for slicing flesh. They are engineered to saw through bone, shell, wood, and occasionally even man-made materials. The edges of each tooth form cutting surfaces that tear rather than stab, allowing the shark to dismantle sea turtles, the armored fish of reef environments, and the thick hides of marine mammals. The teeth are also replaceable. A single shark may cycle through thousands of teeth during its lifetime, ensuring that the wear and tear of an exploratory lifestyle never dulls its primary sensory instrument. Tiger sharks are known for what researchers call test biting, a behavior rooted in both curiosity and opportunistic feeding. When the shark encounters an unfamiliar object, a floating log, a sea turtle shell fragment, a camera housing, a surfboard, or a snorkeler, it may circle, bump lightly, and finally engage with a tentative but substantial bite. This bite is not a warning bite in the way some smaller sharks deliver defensive nips. It is an examination. The shark tastes pressure, density, texture, and chemical composition all at once. In the vast ocean where food is unpredictable and scents disperse quickly, this method of sampling expands the shark's ability to evaluate potential nourishment. Unfortunately, this same exploratory bite, even when not driven by predation, can inflict catastrophic injuries. The force behind a tiger shark bite is immense. The muscles surrounding its jaws anchor directly into reinforced cranial structures, allowing the shark to clamp and twist with substantial torque. When combined with the saw-like motion produced by the head swing, the impact of a single bite can remove large sections of tissue. What is particularly dangerous is the margin for error. There is none. Even a cautious bite produces levels of trauma that exceed the threshold of survivability for many marine animals, and for humans, it often results in profound damage, even if the shark releases immediately afterward. The serrated teeth produce lacerations rather than punctures, enlarging wounds and complicating treatment. A curious bite can become a fatal event, not because the shark intended harm, but because its biology does not allow for gentle exploration. Tiger sharks do not appear suddenly out of emptiness. They move with a logic shaped by ecology. Their patrol routes often align with the movements of other species. After storms, they approach shorelines where seabirds crash into the surf. At night, they swim along reef edges to intercept sleeping fish or weakened turtles. In river mouths and estuaries, they follow scent trails from carrion washed downstream. They are equally comfortable in turquoise shallows and deep blue pelagic zones, a versatility matched by few other predators. This adaptability brings them into areas frequented by humans, surfing zones, snorkeling sites, diving locations, and nearshore sandbars where fish aggregate. The visual presence of a tiger shark differs dramatically from that of other large sharks. Whereas great white sharks often maintain cautious distance, tiger sharks approach directly. Their movement is slow and deliberate, conserving energy while displaying confidence. They turn broad arcs, allowing their lateral line to map the pressure fields around them. When they approach, they do not bolt, they glide closer, assessing shapes and silhouettes. It is this proximity, not aggression, that unnerves many encounters. Humans expect predators to behave like terrestrial carnivores, either charge or flee. But a tiger shark's calm inspection reflects a different evolutionary strategy. In a world where visibility varies and prey hides in unpredictable locations, curiosity becomes an adaptive advantage. When one appears in the water beside a swimmer or diver, behavior becomes crucial. Sudden movements, splashing and erratic kicking mimic distress signals from injured prey. Vertical positioning with limbs trailing downward resembles silhouettes that sharks evolved to investigate. Maintaining horizontal posture, moving slowly and keeping the shark in sight, reduces the likelihood of mistaken identity. Tiger sharks respond to body language, not consciously, but through instinctive interpretation of movement patterns. A calm human is more difficult for the shark to interpret. A frantic human triggers sensory cues associated with weakened prey. Spatial awareness matters too. Sharks often approach from below or behind, following the natural ambush strategies they use for marine prey. Turning the body to maintain visual contact changes the shark's interpretation of the encounter. Presenting the front of the body, which for many animals signals awareness and readiness, reduces the chance of a test bite. For divers equipped with cameras or gear, extending equipment toward the shark, rather than retreating, can create non-biological barriers that the shark hesitates to cross. It is not fear, but confusion. Unfamiliar shapes interrupt the shark's spatial mapping. Tiger sharks are not indiscriminate attackers. Misidentification contributes to many unfortunate interactions. Surfboards resemble the silhouettes of injured turtles. Snorkelers wearing black wetsuits resemble fish or seals from below. Shiny equipment reflects sunlight in ways that resemble fish scales. The shark's curiosity compels it to confirm these interpretations, and the only tool capable of such confirmation is its mouth. Yet, despite their reputation, tiger sharks play essential ecological roles. They regulate populations of turtles, rays, and large fish, maintaining balance in ecosystems prone to collapse when top predators are removed. Their scavenging behavior prevents the spread of disease by consuming carrion. They influence the behavior of other species indirectly. Turtles alter their migration timing in response to tiger shark presence, and dugongs modify their grazing patterns, preventing overconsumption of seagrass beds. This phenomenon, known as the ecology of fear, demonstrates that predators shape ecosystems not only through feeding, but through the behavior they inspire in prey species. Removing tiger sharks would create cascading effects across marine food webs. Understanding this ecological significance reframes human interactions. Fear alone fails to capture the complexity of the tiger shark's role. Respect is more appropriate. Respect for a predator navigating the world with instincts refined across millions of years. Humans entering the ocean enter the shark's sensory landscape. Recognizing that curiosity is part of the shark's survival strategy helps explain why encounters unfold the way they do. The ocean at noon shifts in color, the light flattening across the surface as the sun climbs higher. The tiger shark continues its patrol, its silhouette moving between columns of blue. To the shark, nothing extraordinary has occurred. It investigated scents, followed vibrations, and performed the behaviors that allow it to thrive. To a human, however, a close encounter leaves memory etched with equal parts awe and unease. The animal's calmness, its directness, and its sheer physical presence challenge assumptions about danger. Yet the truth remains that a single bite, whether exploratory or predatory, can inflict permanent damage. As afternoon light fades and deeper shadows stretch across the water, the shark glides once more into the open sea, leaving behind no sign of its passing except the hush of displaced water. It will continue its patrol, investigating the unfamiliar, sampling the uncertain, and carrying forward a legacy of curiosity that defines its species. The tiger shark is neither villain nor monster. It is a creature whose biology shapes its behavior in ways that demand humility. In the vastness of the ocean, curiosity has consequences. And when the investigator weighs hundreds of kilograms and wields serrated teeth sharpened by evolution, the cost of misunderstanding becomes gravely clear. The surf zone at dawn is a place of contradictions, where the ocean feels both alive and half asleep. A low murmur rolls through the breaking waves, each crest tinted gold by the rising sun, as sand churns beneath the surface in slow, clouded spirals. Seabirds circle above, scanning for fish pushed toward shore by the first movements of the tide. Farther offshore, kelp forests sway with a rhythmic patience that belies the violence sometimes hidden among their drifting blades. Beneath this shifting mosaic of light and movement, a darker shape begins to emerge, gliding beneath the surface, with an efficiency so complete that nothing in the water betrays its presence. The great white shark, an apex predator shaped by millions of years of evolutionary refinement, approaches the surfline with its usual blend of caution, calculation, and sensory precision. Though it is feared for its teeth, the great white's world is defined not by aggression, but by interpretation. Its survival depends on reading silhouettes, vibrations, and scent trails with accuracy. Yet mistakes occur, and in the surf zone where water clarity collapses into turbulence, even a creature of such expertise can be deceived. From below, the view upward is distorted by refraction, glare, and the chaotic interplay of foam and shadow. In these conditions, the silhouette of a surfer paddling on a board resembles the outline of a pinniped, a seal or sea lion, especially when limbs hang over the sides in a way that mimics flippers. Seals form a major component of the great white's diet in many regions, particularly where cold, nutrient-rich waters support large colonies. These animals are agile, strong, and wary. To catch them, a shark must attack with overwhelming speed from below, leaving no time for evasion. When a silhouette matches the right proportions and movement profile, the shark interprets it through instinct rather than conscious analysis. The surf zone, therefore, becomes a place where the animal's sensory toolkit functions at a disadvantage. Reduced visibility forces reliance on shape and vibration alone, and this is where mistaken identity becomes a deadly possibility. The typical attack pattern of a great white shark reflects the predator's need to conserve energy while maximizing success. It begins with a stealthy approach from depth, often angled upward, so the sunlight above outlines the target. The shark accelerates during the final seconds, using powerful strokes of its crescent tail to launch its body toward the surface. When the jaws open, rows of serrated teeth designed to slice rather than puncture form a semicircular trap. The first strike is decisive, a single forceful bite delivered with momentum that can catapult the shark partially out of the water. This is not random violence. It is a hunting technique perfected against prey, capable of inflicting injury if the shark were to engage in prolonged struggle. For seals, the initial bite causes massive tissue damage and bleeding. Once the target is immobilized, the shark releases it and circles, waiting for weakness or loss of consciousness to follow. Only then does it consume the prey. This strategy protects the shark from injury while ensuring a manageable meal. But when the shark realizes the object it has bitten is not what instinct predicted, when the texture, taste, density, or resistance does not match mammalian flesh, it often disengages. Humans do not resemble seals in chemical composition or overall structure. A shark sampling human tissue detects the mismatch quickly, and in many documented cases, it swims away after the initial bite. Yet even a single exploratory bite from a great white shark can be catastrophic. The force of the attack, amplified by the shark's momentum, can remove entire sections of muscle, fracture bone, and sever blood vessels critical for survival. The serrations on the teeth act like miniature saws, tearing through tissue with efficiency unmatched by most other predators. For a human, survival depends on immediate rescue, rapid blood loss control, and swift transportation to medical care. Shock becomes a secondary threat, an involuntary physiological response that can shut down circulation, obscure cognitive function, and accelerate decline. Even when the shark is no longer interested, the consequences of that first encounter continue to unfold with frightening momentum. Understanding great white shark perception helps explain why such attacks often occur during specific conditions. Low visibility increases the likelihood of misinterpretation. Dawn and dusk amplify contrast while diminishing detail, making silhouettes more ambiguous. Turbid water stirred by surf, storms, or river outflow reduces clarity to the point where the shark must rely heavily on vibration and movement patterns. Surfboards, bodyboards, and even swimmers create wave signatures that approximate those of injured seals, a sound profile that triggers investigation. When multiple sensory cues align incorrectly, the shark commits to the strike. The surf zone also represents a natural hunting corridor. Seals frequently enter shallow waters to rest, feed, or escape larger predators. In many regions, shifting sandbanks create channels that funnel prey into predictable pathways. Sharks learn these patterns. Their patrol routes often include repeated laps through the same regions of coastline, especially near seal rookeries. This does not mean sharks are targeting humans deliberately. Rather, humans place themselves in areas where shark hunting strategies are already well developed. Group presence influences shark behavior in subtle ways. Multiple surfers create distortion fields that confuse the shark's assessment. A cluster of swimmers appears less like solitary prey and more like a mixed signal that does not fit evolutionary templates. Sharks are more likely to approach lone individuals whose silhouettes stand out cleanly against the surface. This is why safety guidelines emphasize staying in groups when possible. From the shark's perspective, confusion leads to caution, and caution reduces the probability of a test strike. Certain environmental signs can also predict risk. Flurries of seabird activity often indicate fish pushed toward the surface, attracting both seals and sharks. Seal presence itself is a potent signal. Anywhere seals gather, great whites maintain a ghost-like presence at varying distances. Even water temperature matters. Colder water draws sharks closer to shore in many regions because their prey behaves differently under those conditions. Human understanding of these patterns remains incomplete, but decades of observations show that great white shark encounters rarely occur in isolation from broader ecological rhythms. Despite their fearsome reputation, great white sharks do not linger near humans after realizing their mistake. Most attacks follow the hit-and-release pattern, with the shark swimming away before the victim even surfaces. In deeper water, the shark may circle out of curiosity, but prolonged engagement with humans is uncommon. Predators evolve to minimize wasted effort, and humans provide little reward. Yet the mechanics of the initial bite leave little margin for recovery. The combination of shock, hypothermia, hemorrhage, and remote rescue conditions often determines outcome long before medical personnel arrive. This distinction between intentional predation and mistaken identity remains essential to understanding the species. Great white sharks are apex predators, responsible for regulating marine ecosystems through complex interactions. Their presence controls seal populations, indirectly shaping fish dynamics and kelp forest resilience. Removing sharks disrupts this balance, leading to cascading ecological effects. Fear-driven culling efforts of past decades reduced shark numbers dramatically, prompting long-term scientific concern. Sharks are not villains, they are keystone species whose ecological influence extends far beyond the surf line. Behavioral adjustments allow humans to coexist with these predators more safely. Avoiding the water during dawn and dusk, remaining in groups, staying out of areas with active seal movement, and refraining from wearing shiny objects that imitate fish scales all reduce risk. Surfers and divers who understand the sensory world of the shark, its reliance on contrast, vibration, and silhouette, place themselves at lower probability of mistaken identity. Respecting the natural hunting corridors of great whites means recognizing when the ocean is sending signals that conditions are not favorable. As midday light spreads across the surf and the water grows clearer, the great white retreats toward deeper slopes where visibility improves and prey becomes more recognizable. Its outline fades into the cobalt shadows, the massive tail sweeping with slow, measured rhythm. The shark has made no mark on the surface, no disturbance that betrays its passing. It lives in a world governed by instinct, pattern, and sensory convergence. A world where mistakes are rare but never impossible. For the humans who enter that realm, awareness becomes the dividing line between awe and risk. The great white shark does not hunt humans. It hunts silhouettes, vibrations, and opportunities dictated by the rhythm of the sea. But when those signals overlap imperfectly, the consequences can be life-altering. Mistaken identity may explain the behavior, yet real teeth define the outcome. A reminder that in the ocean's shifting, refracted landscape, survival hinges not on malice or intent, but on the precarious interplay between perception and reality. The surface of the water looks peaceful in the early morning, when sunlight first begins its slow descent through the upper layers of the sea and ignites the world below in shards of trembling silver. Small baitfish gather near the surface, schooling tightly as they ride the boundary between light and shadow. Their scales catch the sun at scattered angles, sending tiny flashes into the water, signals that the human eye barely perceives, but which act as beacons to one of the most explosive predators on the reef. Far below, drifting just above the sandy valleys between coral ridges, a barracuda hangs motionless in the water, its long body suspended with effortless precision. It does not paddle or sway. It simply exists, holding position through micro-adjustments so subtle they are almost invisible. The fish's silver flanks reflect the filtered light like polished metal, and its elongated shape resembles a bolt of sharpened muscle waiting for a reason to ignite. The barracuda's stillness is not laziness, it is economy. This predator has refined ambush hunting to an art form, choosing not to waste energy on unnecessary movement. Instead, it monitors its surroundings with large, forward-facing eyes, capable of discerning the glint of a scale from many meters away. In a world where survival hinges on reaction time, the barracuda's visual acuity functions like a finely tuned sensor. What interests it most is contrast, rapid shifts between dark and light, sudden flashes, and the erratic vibration signatures produced by prey in distress. Among these cues, one stands paramount: the shimmer of reflected light. Evolution has tied these flashes directly to the movement of wounded fish, and the barracuda interprets them as signals of opportunity. Unfortunately for humans, this instinct extends beyond natural prey. Anything shiny, dive knives, camera equipment, watches, necklaces, even the glint of a swimming fin, can trigger the animal's attention. The predator's body is built for speed that defies intuition. Its long, streamlined profile minimizes drag, while powerful muscles along the midsection act like biological springs. When a barracuda decides to strike, it ejects itself forward in an explosion of acceleration, reaching impressive speeds over short distances. The strike is so fast that it appears as a blur. One moment the fish is still, the next it has crossed several meters with deadly precision. This acceleration is not merely quick, it is nearly instantaneous. The time between stimulus and attack is so short that many victims recall seeing the fish only after it has already struck. The barracuda's predatory design includes a triple advantage: speed, visual sensitivity, and most critically, a mouth lined with razor-like teeth, engineered not for crushing, but for slicing. The jaw of a barracuda is a mechanical marvel. Its teeth are long, sharply pointed, and arranged in a pattern that resembles the blades of a guillotine. The upper and lower jaws interlock perfectly, with larger fang-like teeth at the front and a series of smaller but equally sharp cutters along the sides. Unlike the serrated teeth of sharks, barracuda teeth are smooth-edged, allowing them to shear through flesh with minimal resistance. This design enables the fish to amputate chunks of its prey cleanly, often decapitating or bisecting smaller fish in a single lunge. When such a jaw meets human skin, the result is catastrophic. Lacerations from barracuda strikes are deep, precise, and often accompanied by significant blood loss. Because the attack relies on speed and slicing rather than a drawn-out bite, the injuries occur in an instant, long before the swimmer has time to react. Human interactions with barracudas typically stem from misunderstanding their behavior. Unlike sharks, barracudas do not rely on scent trails to hunt. They engage visually, responding to cues that mimic struggling prey. Divers and snorkelers who wear reflective accessories unintentionally replicate the same visual triggers that baitfish emit when caught in sunlight. Even the flash of a spear gun tip, the glint of a metal snorkel buckle, or the sparkle of an underwater camera can attract the attention of a curious barracuda. The fish is not drawn by aggression, but by instinctive reaction. It sees a potential feeding opportunity and investigates. Barracudas also interpret rapid movement as vulnerability. When swimmers thrash or kick vigorously in murky water, their limbs produce unpredictable flickers and turbulence. To a barracuda, these disturbances resemble the frantic motion of an injured fish fleeing a predator. The combination of flashes and erratic motion forms a near-perfect lure, drawing the fish closer as it attempts to decipher whether the phenomenon represents food. Many barracuda strikes on humans occur when the water is cloudy or visibility is low, amplifying the reliance on silhouettes and flicker cues. Under these conditions, the fish cannot distinguish between prey and non-prey until the moment of impact. The ecosystem in which barracudas operate contributes to this dynamic. They prefer zones of transition, edges of reefs, drop-offs, mangrove channels, and areas where currents deliver schools of baitfish. These are also areas snorkelers and divers frequent for their biodiversity. Juvenile barracudas patrol shallow seagrass beds and calm lagoons, while larger individuals hover in deeper blue water just beyond the reef crest. In many tropical destinations, the sight of a meter-long barracuda drifting motionless is common enough that locals hardly react. Yet this composure masks a predator capable of accelerating from absolute stillness to striking velocity in a breath. Barracudas also exhibit a unique predatory strategy that blends stalking and ambush. They often tail groups of fish for extended periods, waiting for a moment when one individual breaks formation or flashes unexpectedly. Their approach is selective and opportunistic rather than aggressive. When the opportunity arises, the attack is so sudden that prey have little chance of escape. The same instinct governs their interactions with humans. They are not territorial, nor do they perceive humans as competition. Instead, they focus on patterns that match their neurological blueprint for food. A single flash, whether from a fish or a piece of jewelry, is enough to activate the reflex. Injuries from barracuda attacks vary, but they share common characteristics: clean cuts, rapid blood loss, and the psychological shock of an event that occurs faster than comprehension. Some victims suffer severe hand injuries after reaching toward fish or coral with shiny tools. Others are struck on the leg or foot while swimming near schools of baitfish. In rare cases, barracudas leap toward objects above the surface, driven by the same visual cues they respond to underwater. Although fatalities are extremely uncommon, the speed and violence of the strike leave lasting trauma, both physical and mental. Unlike territorial predators or ambush specialists that defend fixed hunting grounds, barracudas respond almost exclusively to sensory triggers. This makes prevention straightforward when understood properly. Removing shiny objects is the most effective measure. Watches, necklaces, bracelets, rings, and reflective equipment transform swimmers into unintentional lures. Avoiding rapid, chaotic movement in murky water also reduces risk, as does refraining from swimming near large schools of baitfish or during low visibility conditions. Calm, deliberate movement communicates that the swimmer is not prey, reducing the likelihood of a reflex strike. Despite their reputation, barracudas are indispensable components of tropical marine ecosystems. They regulate populations of smaller fish, preventing explosive growth of species that might otherwise overwhelm reef habitats. Their presence influences prey distribution, contributing to the balance between predators and grazers. They are not confrontational animals. They simply follow sensory algorithms written by evolution. Misinterpretation of signals, by them or by humans, creates the overlap that results in injury. As midday light intensifies and the ocean turns from silver to sapphire, the barracuda's silhouette sharpens into a long, glinting spear drifting just beyond the reef. It surveys the water with practiced patience, waiting for the next flash to break the monotony of the sandscape. It is a creature built for moments, not pursuits. When the moment comes, its body will compress, release, and propel forward faster than the human eye can track. When the moment passes, it will return to stillness, as though nothing occurred. The barracuda does not hunt humans, nor does it seek confrontation. It responds to signals: light, movement, contrast, interpreted through the lens of a predator evolved for precision. To share the water with such an animal is not an act of bravery, but of awareness. The shimmer of sunlight on metal may be beautiful to us, but in the liquid world of the barracuda, beauty is indistinguishable from opportunity. And when that opportunity arrives in the form of a misplaced glint, the ocean's lightning bolt answers with the only language it knows: speed, accuracy, and an opening of jaws lined with blades. The reef at dusk feels like a vast living cathedral preparing for its nightly shift. Sunlight dissolves into amber ribbons that stretch across the corals before fading into the darker blue of approaching night. Planktivorous fish gather in the water column, sensing the rise of nocturnal predators. Soft corals sway with the first long surge of evening tides, releasing chemical signals that drift through the labyrinth of tunnels and crevices carved over centuries. In this shifting half-light, one of the ocean's most misunderstood hunters stirs within its narrow chamber. A moray eel, its body concealed deep inside a limestone corridor, inches forward with the slow, coiling precision of an animal shaped for tight spaces. Only the blunt snout and open mouth break into the visible world, illuminated by the final glow of the day. It opens and closes its jaws in a steady rhythm that appears threatening, but is simply the eel's method of breathing, drawing water through the mouth and across the gills. Yet the motion, paired with the creature's needle-like teeth, evokes an ancient menace. The moray has no need to feign aggression. It simply waits for darkness, when the reef becomes an arena for ambush hunters. The anatomy of the moray eel is a masterclass in evolutionary specialization. Its elongated body, lacking pectoral fins, allows it to navigate tunnels that would trap larger or bulkier predators. Its skin, coated with protective mucus rather than heavy scales, reduces friction against jagged rock. But it is the mouth, both the visible jaws and the hidden pair behind them, that defines the moray's hunting strategy. The outer jaws are equipped with recurved teeth that angle backward, forming a natural trap. Once something enters the moray's mouth, these teeth prevent escape by anchoring the prey in place. Unlike fish designed for chewing or crushing, the moray's teeth are meant for gripping, puncturing, and guiding food into the throat. But the true evolutionary marvel lies deeper, past the line of sight. The moray eel possesses a second set of jaws, pharyngeal jaws, anchored within the throat. These jaws are capable of lunging forward like a biological grappling mechanism, seizing prey and pulling it deeper into the digestive tract. This unique adaptation makes morays among the only vertebrates that can project their pharyngeal jaws outward to transport prey inward. In the dim light of the reef, this hidden system becomes a deadly advantage. When a small fish passes near the entrance of a moray's shelter, the eel strikes with surprising speed. The outer jaws clamp down, holding the prey in a cage of curved teeth. Then, a moment later, the pharyngeal jaws surge forward, grasping the prey with additional needle-like teeth before retracting with a powerful contraction. The combined motion drags the victim deeper inside the eel's throat, eliminating the need for suction-based feeding. For a creature that spends much of its life in narrow crevices, this mechanism provides a feeding strategy perfectly matched to its environment. It does not chase prey across open water. It drags prey inward towards safety and devours it within the walls of its rocky fortress. This anatomy also explains why moray bites on humans are so severe. When a moray clamps onto a hand, arm, or finger, the backward-pointing teeth create puncture wounds that tear when the victim tries to pull away. The eel's instinct to retract its prey into its den causes it to twist and anchor its body, making escape nearly impossible without causing additional injury. In some cases, the pharyngeal jaws engage automatically, amplifying the depth of the wound. This reflex does not differentiate between a fish and an exploring human finger. It simply follows the neural pathways built for feeding. The result is a bite that does not release easily and often causes severe tissue trauma. Human interactions with morays often stem from curiosity or misplaced confidence. Divers and snorkelers, enchanted by the eel's striking appearance, a pattern of greens, browns, yellows, and blues depending on species, approach too closely, assuming that a stationary animal is harmless. Many tourists feed morays by hand, a practice that encourages the eel to associate human movement with food. In these cases, the eel's vision becomes an important factor. Morays have poor eyesight and rely heavily on scent to locate prey. When a hand holding food drifts near the entrance to a den, the eel detects chemical cues and strikes toward the general direction rather than the exact target. The result is predictable. The eel misses the food and bites the hand. Because the teeth are angled to prevent escape, what begins as a feeding mistake quickly becomes a severe injury. Moray bites also carry another layer of danger: infection. The eel's mouth contains bacteria adapted to the decomposition of fish and the breakdown of organic material. These microorganisms thrive in the mucus-coated environment of the eel's oral cavity. When the teeth puncture human skin, bacteria are introduced deep into the tissue, creating a high risk of infection even if the injury initially appears mild. The deep, narrow punctures facilitate bacterial growth by creating isolated pockets of tissue that are difficult to clean. In severe cases, infection can lead to tissue necrosis, prolonged swelling, and long-term mobility issues in hands or fingers. Divers often recount that the bite itself is less harmful than the days and weeks of treatment needed to manage the resulting infection. Beyond curiosity, another source of risk comes from the structure of the reef ecosystem. Many reef organisms hide under rocks, inside crevices, and within coral formations. Snorkelers reaching into holes to steady themselves during strong currents, or divers searching for lobsters may inadvertently place their hands in front of a waiting moray. The eel does not attack out of territorial aggression. It reacts to sudden tactile stimulus at the entrance of its shelter, the same signal that would precede the arrival of prey. To the moray, a hand entering the den resembles a fish snapping at the entrance, and the instinctive response is to strike first. The aftermath is often far worse than the diver anticipates. Fingers can be severed, tendons torn, and joints damaged as the eel thrashes to pull the perceived prey deeper into its lair. Environmentally, the moray eel plays a critical role in maintaining reef balance. It regulates populations of smaller fish and crustaceans, helping control species that might otherwise overwhelm the ecosystem. By hunting at night and retreating by day, the moray occupies a temporal niche that complements daytime predators. This rhythm ensures that predation occurs across a full 24-hour cycle, contributing to the overall stability of the reef. Morays also engage in surprising, collaborative behaviors such as cooperative hunting with groupers. In these interactions, groupers signal morays with body movements, inviting them to join in hunting sessions where each species leverages its strengths, the grouper driving prey into crevices and the moray extracting them. This mutualistic strategy demonstrates a level of ecological sophistication rarely appreciated by casual observers. Despite this ecological importance, morays remain misunderstood. Their open-mouthed resting posture gives the illusion of perpetual aggression, when in reality it is a physiological necessity for respiration. Their serpentine movements evoke fear even when the eel is simply navigating its home. Their sudden emergence from holes creates dramatic images that overshadow their role in maintaining reef health. But it is crucial to remember that morays are ambush predators, not indiscriminate attackers. Most injuries stem from human misjudgment, not eel aggression. As night fully settles over the reef, the moray eel leaves its den with slow, controlled undulations. Its eyes adjust to the darkness, its body weaving through coral formations with the confidence of an animal that knows every contour of its environment. It moves without sound, without disturbance, following the scent of prey along invisible chemical pathways. For the eel, the night is a time of opportunity, not danger. For humans who enter this realm unaware, the night holds risks shaped by instincts older than our species. The rule, as ancient as the reef itself, remains uncomplicated. Do not place your hand into a hole you cannot see fully inside. Within the ocean's hidden architecture, some tunnels belong to creatures that grip first and question later. And once the moray eel closes its jaws, outer and inner, the ocean becomes a place where release is no longer guaranteed. The shallow reef flats shimmer under the harsh brightness of midday, where sunlight penetrates almost vertically and scatters across the sand in trembling ribbons of gold. Here the water is warm, deceptively calm, and broken only by the gentle sway of seagrass and slow pulses from darting schools of juvenile fish. The place looks peaceful to the untrained eye, an underwater meadow where nothing dangerous seems to lurk. But beneath a small ridge of cracked coral rubble, inside a burrow no wider than a clenched fist, a creature waits with a level of coiled violence that contradicts its size entirely. Only two small periscoping eyes protrude from the entrance, each one rotating and tilting independently like miniature tracking devices surveying the world. This is a mantis shrimp, and while its body is barely the length of a human hand, its strike is powerful enough to fracture aquarium glass, split crab shells cleanly in half, and, in the wrong circumstances, break human bone. The mantis shrimp's reputation seems almost exaggerated, but the truth is more astonishing than the myths. Evolution has turned this animal's raptorial appendages into biological weapons, capable of delivering one of the fastest movements ever recorded in the natural world. These limbs, folded tightly against the body like cocked hammers, are loaded with a network of spring-like structures made from a natural polymer that stores elastic energy. When released, the limb accelerates with such force that water cannot move aside quickly enough. Instead, the limb outruns the water, creating pockets of vapor known as cavitation bubbles. These bubbles collapse instantly, producing shock waves and flashes of heat that add a secondary impact nearly as damaging as the strike itself. A mantis shrimp punch is not merely a blow, it is a combined physical and explosive event, occurring in a fraction of the time it takes the human eye to blink. Within the burrow, the mantis shrimp rocks gently, adjusting its stance as if calculating trajectories. It is a creature of precision as much as power. Its compound eyes are among the most advanced in the animal kingdom, capable of detecting polarized light, ultraviolet wavelengths, and subtle variations in color that most marine species cannot perceive. Each eye moves independently, creating a three-dimensional map of the surroundings while also narrowing in on micro-movements. Sand displaced by a passing crab, the trembling of a small fish seeking shelter, or the silhouette of a snail crawling too close to the entrance. These sensory abilities do more than prevent starvation. They ensure that the mantis shrimp can strike with absolute accuracy. Its punch lands precisely where it intends, often hitting the same location multiple times with surgical consistency. Slow-motion footage reveals what the human observer cannot see in real time. When a mantis shrimp attacks a crab, the first blow lands with staggering velocity, cracking the shell with a sound like snapping twigs. The crab recoils, but the shrimp has already launched its second strike. Each impact creates bursts of cavitation, small implosions that momentarily heat the surrounding water to temperatures comparable to the surface of the sun. Though brief and localized, these bursts amplify the damage. They also produce flashes of light, a phenomenon known as sonoluminescence, which would be invisible to most creatures, but not to the mantis shrimp's complex eyes. The shrimp may literally see the light generated by its own strikes as it dismantles its prey. These attacks are not random. The mantis shrimp is a tactical predator. It knows where the exoskeleton of its prey is strongest and where it is weakest. A crab's claws are reinforced by dense calcified layers, but the joints along the underside of the body are more vulnerable. A snail's shell is strongest near the apex but fragile near the lip. The mantis shrimp targets these zones with mechanical efficiency, repositioning its body to strike from angles that maximize leverage. This precise targeting allows the shrimp to kill prey much larger than itself. Within minutes, what began as a robust armored animal becomes a broken assemblage of shell fragments and exposed flesh. This makes the mantis shrimp a fascinating but dangerous animal for divers and aquarium keepers. The creature's burrow may look like an inviting hole in the rock, something interesting to inspect or touch. A diver, unaware of what lurks inside, might steady themselves by placing a hand near the entrance. The mantis shrimp perceives the sudden movement as a threat or as prey. Its limb fires, and the diver feels a sharp, instantaneous pain. In severe cases, the strike can break small bones in the fingers or hand, split fingernails cleanly apart, or create deep, bloody lacerations. The injury is not merely the result of impact. Cavitation bubbles can damage tissue beneath the skin, creating bruising and swelling far beyond the point of contact. There are documented cases of aquarium glass cracking or shattering from a mantis shrimp repeatedly striking its reflection, interpreting it as a territorial rival. The most dangerous encounters occur when people try to capture or handle mantis shrimp directly. Their speed is so great that even experienced marine collectors misjudge it. A shrimp lying still on sand can strike before a hand reaches halfway toward it. The reflex is automatic and does not require calculation. The shrimp's nervous system is wired for rapid activation, allowing it to deploy its weapon almost as a single pre-programmed motion. Picking one up barehanded is an invitation to injury, yet the animal's vivid colors often fool observers into complacency. Many species are brightly patterned with bands of green, orange, red, and blue, giving them a deceptively ornamental appearance. But beneath that color lies the explosive potential of a creature evolved for close-quarters combat. The mantis shrimp's ecology reveals why such extreme weaponry developed. Life on the reef is competitive, and many organisms rely on shells, armor, and hiding places to survive. To feed on heavily armored prey, snails, crabs, clams, and other shelled invertebrates, an animal needs specialized tools. Crushing claws exist in larger predators like lobsters, but these claws trade speed for force. The mantis shrimp represents a different evolutionary solution: deliver maximum force in minimum time. The reef environment, with its tight spaces and abundant hard surfaces, favors animals that can strike quickly before prey escapes into a crevice. The mantis shrimp's compact body, spring-loaded limbs, and advanced eyesight make it uniquely capable of thriving in this environment. Interestingly, Not all mantis shrimp species are smashers. Some are spearers, with raptorial appendages shaped like barbed blades used to impale soft-bodied prey such as fish. These species strike with similar speed, but rely on piercing rather than impact force. Smashers, however, are the ones responsible for broken aquariums and shattered shells. Their clubs are reinforced with layered mineral composites, making them among the toughest biological materials known. Research into these structures has inspired engineers seeking to design advanced armor and impact-resistant materials. The same qualities that allow the shrimp to punch through shell and bone make its appendages resistant to the stress generated by repeated impacts. While most biological tissues would fracture under such forces, the mantis shrimp's club flexes just enough to prevent catastrophic failure. As daylight fades and the reef transitions toward evening activity, the mantis shrimp becomes more active. It emerges from its burrow, creeping along the sand with cautious, probing movements. Its eyes scan every direction simultaneously. Its body sways with controlled tension, like a coiled spring in motion. When it encounters an object of interest, an empty shell, a small piece of coral, or the discarded carapace of a crab, it tests it with light taps of its club. These investigative touches reveal density and resonance, helping the shrimp evaluate whether the object could serve as future shelter material or whether it might conceal hidden prey. The touches are gentle, a stark contrast to the violent strikes the animal is capable of delivering when opportunity arises. This juxtaposition, slow, deliberate motion paired with the capacity for sudden force, defines the mantis shrimp's existence. It is neither aggressive nor unpredictable. It simply responds to sensory information with precision and power. For humans entering its world, the lesson is clear. Admire from a distance. Never reach into holes. Never attempt to handle a mantis shrimp directly. And never assume that a small size equates to harmlessness. In the reef ecosystem, danger often comes in small packages, and few creatures embody that truth more completely than the mantis shrimp. Beneath its vibrant colors and complex vision lies a weapon refined by evolutionary necessity. When the mantis shrimp strikes, the ocean momentarily trembles. Water flashes, shells rupture, and even the hardest surfaces reveal their limits. It is a reminder that the smallest animals often carry the biggest surprises, and among them, the mantis shrimp stands unmatched. The coastline looks gentle in the early morning, when warm air begins to rise off mudflats and mangrove swamps like a soft exhale from the earth itself. Tidewater slides across the sand with a thick, syrupy slowness that suggests nothing dangerous beneath its surface. Mangrove roots curve upward like arched fingers, holding pockets of brackish water in sheltered basins that glow brown and green under the first light. Birds call across the estuary, sending echoes through the dense canopy, while mullets splash in predictable arcs as they leap from predators below. To the untrained visitor, these environments seem quiet, almost serene. But beneath the film of calm water, pressed against the muddy bottom with the patience of a creature that measures time in decades rather than moments, lies one of the most proficient ambush hunters on the planet. A saltwater crocodile, motionless in the murk, inhabits this threshold between river and sea, watching the world with eyes that barely break the surface. The crocodile's presence is nearly impossible to detect. Its body is submerged, only the eyes and nostrils exposed, positioned on top of the skull like two small sensors designed for stealth. The water around it is opaque, churning with sediment and decaying leaves carried downstream. Visibility drops to nearly nothing, transforming the crocodile's world into a realm of sound, vibration, pressure shifts, and chemical cues. This animal does not need clarity. It evolved for darkness, for environments where turbidity hides both predator and prey. Sharks rely on open water, on silhouettes edged by sunlight. Crocodiles rely on invisibility, letting the environment conceal them entirely. In the brown water of river mouths and estuaries, the crocodile becomes a shadow among shadows, waiting for the precise moment when opportunity drifts within strike range. The crocodile's patience is legendary. It can remain still for hours, expending almost no energy, regulating its metabolism through behavioral thermoregulation. By basking in sunlight on riverbanks or absorbing warmth from shallow water, it maintains body temperature with minimal effort. When temperatures drop, it slows its movements even further. This energy-efficient lifestyle allows crocodiles to thrive as ambush predators, conserving strength for the only moments that matter, the explosive seconds in which they attack. A crocodile does not chase, it launches. The distinction is important. A chase requires energy, strategy, and risk. A launch demands only positioning, timing, and the reflexes of an animal that has perfected the strike over millions of years. When something, an animal, a bird, a dog, or a human, moves close to the water's edge, the crocodile senses it long before visual contact. Pressure waves produced by footsteps travel across the water as vibrations. The crocodile's highly sensitive integumentary sensors detect these ripples, creating a spatial map of nearby movement. Chemical traces wash into the water, carried by microscopic skin particles and environmental debris. Temperature gradients form around warm bodies entering the cool estuary. These cues converge, signaling to the crocodile that something living is within reach. It adjusts its buoyancy slightly, rises a few centimeters, positions its limbs beneath its torso, and prepares. The ambush begins in absolute silence. There is no warning swirl or hint of motion. When the strike comes, it is instantaneous, a violent surge of muscle that propels the crocodile upward and forward with extraordinary precision. Its jaws snap shut with immense force, generated by massive muscles along the skull and neck. The bite is not simply strong, it is engineered to crush bone. Once the crocodile clamps onto its target, escape becomes almost impossible. The animal's teeth, conical and deeply set, are not designed for slicing but for gripping. They latch onto flesh and bone with a locking strength that few animals on Earth can match. What follows is the signature behavior that defines crocodile predation, the death roll. The crocodile twists its body with a rapid spiraling motion, using its powerful tail to generate torque. This motion tears flesh, dislocates joints, and incapacitates prey. In water, where buoyancy shifts weight and momentum, the death roll becomes devastating. The victim is pulled off balance, submerged, and overwhelmed by force and disorientation. For humans, the roll is nearly always fatal, not because the crocodile seeks to kill quickly, but because drowning occurs long before the predator releases its grip. Fighting back is pointless. No amount of strength or struggle compares with the crocodile's ability to anchor itself with its tail and limbs while twisting its massive body around the axis of its jaws. The danger of crocodile territory lies not only in the animal's power, but in the unpredictability of the environment. River mouths, estuaries, mangrove swamps, and tidal inlets form dynamic landscapes where fresh water meets salt water. These zones attract a diversity of animals, fish moving upstream to spawn, birds hunting crustaceans, mammals foraging at low tide. Humans too find these areas appealing for fishing, swimming, or cooling off on hot days. But in regions where crocodiles live, these same environments form the core of the animal's hunting grounds. Mangroves, in particular, create a maze of roots and shadows that conceal crocodiles perfectly. The dense network of trunks and branches provides cover for both predator and prey, but it also eliminates open escape routes. Shallow channels between root systems funnel animals into narrow corridors where a crocodile can lie in wait. When the tide rises, crocodiles use the increased water depth to travel silently through the mangroves, moving with minimal disturbance. When the tide falls, they retreat to deeper pools, maintaining access to ambush positions near pathways used by terrestrial animals. Their movements are tied to tidal rhythms, feeding opportunities, and thermal preferences. But from a human perspective, these rhythms often remain invisible until too late. The comparison between sharks and crocodiles highlights the ecological divide between open water predators and ambush specialists. Sharks hunt in clear or semi-clear water, relying on contrast and motion to identify targets. Their attacks often stem from misinterpretation, a silhouette mistaken for prey. Crocodiles, by contrast, require no guesswork. Their prey steps within centimeters of their jaws. The murky water that obscures visibility for humans offers perfect camouflage for crocodiles, who have evolved to function in environments where sight is secondary. Sharks approach from below. Crocodiles attack from the edge. Sharks retreat after a test bite. Crocodiles commit fully, holding tight until their prey ceases struggling. Both predators are apex specialists, but crocodiles operate in the realm of certainty. When a crocodile strikes, it is not confused. It is executing a plan that has worked for millions of years. Crocodiles are not reckless killers. They are strategic survivors. Their hunting methods reflect the constraints and opportunities of their environment. They often target weak, young, or unaware animals, conserving energy by avoiding unnecessary conflict. They rely heavily on stealth, blending into water the color of tea or chocolate. The muddy opacity not only hides the crocodile but also suppresses the sensory world of its prey. Humans stepping into this water have no chance of seeing beneath the surface. The submerged world becomes a void, and within that void, the crocodile holds every advantage. Human encounters with crocodiles often occur at the margins, where land meets water, where people wash clothes, gather water, fish, or cool their bodies. These edges are liminal spaces, dangerous because they bring two ecological worlds into contact. The threat does not come from the open channel where the water is deep, but from the shoreline where the water is shallow enough for humans to stand. Here the crocodile waits, fully submerged, merging with the bottom until movement gives it a target. The human perception of safety near shorelines becomes the precise vulnerability the crocodile exploits. The best advice in crocodile country is simple, yet often ignored. Avoid swimming in river mouths. Avoid wading into turbid estuaries. Avoid mangroves at high tide, and never assume that shallow water means safety. Crocodiles do not need depth to kill. A few centimeters of water are enough for them to strike with lethal force. Their ability to hold their breath for extended periods, regulate buoyancy, and remain undetected makes them unmatched among aquatic predators in terms of ambush capability. As the tide recedes and the sun climbs higher, the crocodile remains beneath the surface, hidden beneath a thin layer of water that looks harmless to the untrained eye. It will continue its slow patrol along the boundary between land and sea, guided by instincts older than human civilization. In this world of brown currents and shifting sediments, the crocodile is not merely a predator. It is the embodiment of the coastal ambush, silent and invisible, until the moment it erupts into motion. To enter this water without understanding its inhabitants is to mistake calm for safety and silence for emptiness. But the estuary never lies idle. Somewhere beneath its surface, a crocodile waits, not out of malice, but because ambush is the language written into its bones, and the murk is the world in which it rules. The seafloor at twilight glows with a muted lunar blue, the kind of color that makes even predator-filled waters feel gentle for a moment. Soft sediment drifts in faint spirals with each passing current, and the reef's edges fade into a calm gradient of deepening shadows. Small fish retreat into crevices, crustaceans begin their nightly march, and bioluminescent plankton spark tiny constellations in the water column. In this quiet hour, among coral shelves shaped like forgotten ruins, a shape emerges that seems more whimsical than dangerous. An octopus, skin rippling through an extravagant palette of textures and colors, flows across the sand like a creature invented by imagination rather than evolution. Its movements are liquid and expressive, each arm exploring with deliberate curiosity, as suckers grip, release, and glide with uncanny precision. To an uninformed diver, the octopus appears harmless, gentle, intelligent, even endearing. But beneath that disarming charm lies a survival strategy built on chemistry, strength, and the precision of a hunter equipped with a weapon few people ever notice: a beak sharp enough to crack crab shells and deliver venom deep beneath the skin. The octopus does not move through the reef with the urgency of a predator on patrol. It explores. Its arms stretch and curl, mapping the environment through touch as much as sight. Each of its hundreds of suckers contains dense clusters of sensory receptors that allow the octopus to taste the world simply by touching it. Every texture, every chemical residue, and every vibration paints a detailed picture. With this tactile intelligence, it identifies prey, distinguishes friend from threat, and navigates narrow openings that would trap most marine animals. The octopus's brain extends into its limbs, granting them a level of autonomy unmatched in the animal kingdom. Each arm can make decisions independently, adjusting grip strength, coordinating movement, or manipulating objects, while the central brain focuses on larger goals. This distributed nervous system allows the octopus to multitask in ways that give it an evolutionary advantage, one that becomes apparent when it encounters both prey and unsuspecting divers. Despite its soft body, the octopus is a formidable hunter. Hidden beneath its massive arms, concealed at the center of its muscular web, lies a beak made of chitin, a substance harder than bone and nearly impossible to break. This beak, resembling that of a parrot in miniature, can pierce through the shells of crustaceans, the carapaces of crabs, and the tough exoskeletons of lobsters. The bite is precise and deliberate. Once the beak penetrates, the octopus delivers saliva laced with enzymes capable of breaking down flesh and disarming prey. Some species possess mild venom that immobilizes small animals. Others, particularly the blue-ringed octopuses, wield a toxin potent enough to paralyze a human within minutes. Even the harmless-looking species that divers commonly encounter possess beaks strong enough to slice deep into human skin, inflicting punctures that can swell for days and introduce bacteria from the animal's saliva. One of the most striking behaviors observed among octopuses is their willingness to grab onto divers and equipment. They do not do this out of aggression. Curiosity drives them. Their suckers explore metal, rubber, and exposed skin with equal interest, often testing grip strength or investigating reflections in a diver's mask. A small octopus's embrace may feel gentle, almost playful, but a large individual can exert surprising force. Its arms, capable of generating multiple points of suction simultaneously, can anchor onto gear with enough strength to momentarily restrict movement. Divers sometimes find themselves wrestling with an octopus that has taken interest in a shiny buckle, a dangling camera, or a loose fin strap. These behaviors highlight the intelligence of the animal, but they also reveal the risk. An octopus exploring too close to a hand can bite if startled. And unlike the wounds inflicted by fish or crustaceans, an octopus bite is often accompanied by the injection of enzymes that break down tissue, causing prolonged pain and localized swelling. Then there is the creature that shifts the lesson from caution to absolute seriousness. The blue-ringed octopus. No larger than a golf ball, this species hides among rocks, shells, and discarded coral fragments, easily overlooked by divers and beachgoers alike. Its skin remains a muted yellow or beige until disturbed. When threatened or handled, it flashes bright electric blue rings across its body in rapid pulses, a warning signal to back away. Those rings glow not for intimidation alone, but because the octopus possesses one of the most potent neurotoxins found in marine life. Tetrodotoxin, the same compound found in pufferfish, blocks nerve signals by paralyzing sodium channels in muscle tissue. Once introduced into the bloodstream, it prevents muscles from contracting. Breathing becomes impossible. Victims remain fully conscious but unable to move or call for help. In severe envenomations, respiratory arrest can occur in minutes. The danger of the blue-ringed octopus lies not only in the toxin's potency, but in the animal's small size and deceptively calm demeanor. People often pick up these octopuses unknowingly, drawn to their tiny, delicate appearance or unaware that they are touching one at all until the rings begin to flash. Even a single bite can be enough to incapacitate an adult human. There is no antivenom. Treatment relies on maintaining oxygenation until the toxin fades from the body. Every year, near misses occur across reefs in the Indo-Pacific, where snorkelers or tide pool explorers handle small octopuses without recognizing the danger. The animal's beauty becomes its own hazard, a visual lure masking a biological weapon hidden behind the smallest of beaks. Even non-venomous octopuses pose risks that are commonly overlooked. Their suckers can create strong suction against the skin, leaving bruises or abrasions. Their arms can entangle with hoses, dive gauges, or underwater cameras, making it difficult for divers to move freely. And their intelligence means they sometimes engage in behaviors that mimic play, but can escalate unpredictably. An octopus may investigate a diver's gloved hand, then suddenly seize it, interpreting the movement as either threat or prey. A startled octopus may respond with a reflexive bite. In captivity, aquarists often wear thick gloves, not because the animals are aggressive, but because their curiosity results in unintended injuries. In the wild, divers rarely wear such protection, making a curious octopus encounter far riskier than it initially appears. The octopus's ecological role adds further depth to its story. It is not merely a wanderer of the reef. It is a keystone predator that influences the distribution of crustaceans and small fish. Many species construct dens using rocks, shells, and debris, arranging these materials with deliberate precision to create a secure shelter. Around these dens, accumulations of discarded shells create what scientists call middens, visible evidence of the octopus's feeding habits. These middens reveal what prey species dominate the area, how the octopus manipulates its environment, and how it shapes the balance of the local food web. When an octopus abandons a den, other animals, fish, shrimp, and smaller octopuses, occupy the space, demonstrating the important ecological function of these structures. Yet despite their complexity, octopuses remain vulnerable. Their lifespans are short, often only a few years. Many die after mating or caring for their young, a sacrifice built into their reproductive biology. Their intelligence, remarkable as it is, exists alongside fragility. They are both predator and prey, both powerful and delicate. This duality makes them one of the most compelling creatures in the ocean, and one of the easiest for humans to misunderstand. The ocean twilight deepens into full night, and the octopus retreats toward the safety of its den. Its skin shifts through muted patterns as it blends into its surroundings, each color change guided by chromatophores controlled directly by its brain. It pulls shells toward the entrance, reinforcing its barricade for the evening. Hidden inside, it waits, breathing calmly, its beak tucked away but always ready. The lesson it leaves behind is simple, grounded in biology rather than fear. Never touch an octopus simply because it seems cute, calm, or curious. Beneath its soft exterior lies a weapon honed by evolution, one that can puncture, paralyze, or overpower without warning. In a world filled with creatures whose dangers are obvious, the octopus stands apart as a reminder that intelligence, beauty, and lethality can coexist in the same graceful, mesmerizing form. The shoreline breathes with every incoming wave, exhaling foam across the sand before drawing it backward with a soft rasp that exposes fragments of shells, tangled seaweed, and the tiny tracks of creatures that emerge during the night. Tide pools shimmer beneath the rising sun, their glassy surfaces broken by darting minnows, and the occasional ripple left by something shifting beneath a rock. This is the boundary zone between land and sea, a place where life must endure both pounding surf and scorching sunlight. And patrolling this unstable world with surprising authority are the crabs, armored custodians of the shoreline, sculpted by evolution into compact machines of leverage, muscle, and mechanical power. Their movements may appear comical at first glance, the sideways scuttle that tourists love to imitate, but beneath the familiar exterior lies a creature capable of delivering one of the most dangerous bites in the coastal ecosystem. A crab's claw is not simply a gripping tool. It is a crushing device engineered for violence, capable of exerting forces that can split mollusk shells, sever tendons, and shatter fingernails in an instant. As the morning tide recedes, crabs emerge from crevices in the rocks with purposeful motion, probing the shoreline for food left behind by the night. Their eyes, perched high on stalks, give them a panoramic field of vision, allowing them to monitor predators above while scanning the terrain for edible fragments below. Their antennae flick rapidly, tasting chemical cues dissolved in the air and salt water. Every movement is coordinated with mechanical precision. With each step, their claws hover in front of their bodies, not only for feeding, but for defense, ready to snap shut with astonishing strength if anything strays too close. The muscles controlling the claw, massive bundles packed tightly within the carapace, contract rapidly, generating forces far beyond what their small size suggests. Large species, such as rock crabs and coconut crabs, can exert crushing pressures strong enough to break open hard-shelled prey that would defeat most predators. For humans, the danger lies in underestimating this force. The average beachgoer often views crabs as harmless novelty creatures, forgetting that these animals evolved tools specifically designed to break, crush, and dismantle. A crab does not pinch out of mischief. It pinches because the reflex to clamp onto anything near its claw is as automatic as breathing. When a person reaches toward a crab for a photo, attempting to coax it into a particular pose, the crab interprets the approaching hand as either prey or threat. Its claw snaps shut, and the force travels through the delicate structures of the human finger. Fingernails crack or split, skin tears beneath the pressure. In severe cases, tendons rupture and fractures occur, especially when larger species are involved. Once a crab clamps onto something, release is not immediate. The claw locks shut through a complex arrangement of muscles and joint mechanics, creating a kind of biological vice grip that remains secure even if the crab is lifted, shaken, or submerged. Tourists often make the mistake of teasing crabs for entertainment. They wiggle a shell or stick in front of the animal, unaware that provoking a strike means participating in a contest they cannot win. The crab's claw does not need accuracy, it only needs contact. A split second of carelessness results in an injury that can lead to days of swelling, bleeding, and reduced mobility. Worse still, crab bites often introduce bacteria into the wound. Their claws, used for scavenging rotting matter and prying apart decaying prey, carry microbial communities suited to breaking down organic tissue. When these microbes enter a puncture or laceration, infections occur easily. In tropical regions, where humidity and heat amplify bacterial growth, untreated injuries can develop into abscesses or require medical intervention to avoid long-term damage. The shoreline is full of scenarios that place humans at risk without them realizing it. A child overturns a rock in a tide pool to look for shells. A photographer kneels near a cluster of crabs for a dramatic angle. A diver reaches into a crevice to pick up a pretty piece of coral rubble. In each of these moments, hands enter the defensive perimeter of a crab that was hidden, still, and silent. Crabs are masters of camouflage. Their carapaces often match the rocky textures around them, and their habit of remaining motionless until threatened makes them nearly invisible. When disturbed suddenly, they respond with the instinctive strike that has ensured their survival for millions of years. The mechanical advantage of a crab's claw is rooted in its structure. One side forms a fixed surface, while the other acts like a hinged lever that closes with crushing efficiency. These claws are powered by muscles arranged for rapid contraction and tremendous force, allowing the crab to break open shells far thicker than human skin. Large species can exert pressures comparable to the bite forces of medium-sized vertebrates. Coconut crabs, the largest land-dwelling arthropods, can break open coconuts, a feat requiring power greater than the average human punch. Even the smaller species found along rocky coasts possess enough strength to inflict serious injury. Their claws evolved specifically to fracture hard surfaces. Human fingers offer little resistance. When viewed through an ecological lens, crab behavior becomes not only understandable, but admirable. They are essential recyclers of coastal ecosystems, feeding on detritus, scavenging carcasses, and controlling populations of smaller invertebrates. Without crabs, many beaches would be buried under organic waste. They clean tide pools, aerate sediments, and create burrows that shelter smaller organisms. Their role in the ecosystem is not gentle, it is industrious. They break, crush, and dismantle for the health of the shoreline. Their claws are not weapons in the human sense, but highly adapted tools that allow them to thrive in a world where survival requires both strength and precision. But interacting with such animals requires respect. Shell collectors often lift rocks to search for hidden treasures without considering the creatures that may be sheltering underneath. Crabs respond instinctively to fingers placed near them, grabbing with the same force they reserve for prey. Divers hunting for small souvenirs place their hands blindly into cracks, unaware that a defensive strike in such a confined space can trap fingers between rock and claw, amplifying damage. Even fishermen unloading traps must handle large crabs with caution, using thick gloves or tongs to avoid serious injury. The crab does not aim to harm humans. It simply uses the only defense it has when something enters its space. Scenes of tourists provoking crabs for photos demonstrate how quickly admiration can shift into danger. A person crouches down, edging closer to a large shore crab, waving a hand or object to get its attention. The crab raises its claws in a defensive display, but the tourist interprets it as a comedic pose. They reach closer, trying to adjust the crab's orientation for a better shot. In the next moment, the crab lunges forward, seizing the fingertip. Pain arrives instantly, sharp, crushing, and unexpected. The tourist yelps, jerking backward, but the crab holds on, its claw locked. Panic follows. Blood appears beneath the nail, swelling begins immediately, and the injury turns what was meant to be a light-hearted moment into a medical emergency. Injuries inflicted by crabs differ from those caused by fish or stinging animals. They are mechanical trauma, with crushing forces capable of causing deep bruising, fractures, and tissue loss. Because crab claws often puncture the skin in irregular patterns, cleaning the wound becomes difficult. Salt water introduces additional bacteria, and sand can embed itself deep within torn tissue. The combination of pressure, tearing, and contamination creates the perfect conditions for infection. Medical treatment typically requires thorough cleaning, antibiotic ointment, and careful monitoring for signs of inflammation. In severe cases, surgical intervention becomes necessary to repair torn tendons or remove fragments of crushed fingernail. Despite their strength, crabs do not seek conflict. They retreat whenever possible, scuttling into cracks or burrows at the first sign of danger. Their defensive postures, the raised claws, the sideways sway, are warnings, not invitations. Most negative encounters occur because humans ignore these warnings or approach animals that wish to be left alone. Crabs do not tease or provoke. They defend. They do not choose confrontation, but neither do they hesitate when something violates their sense of safety. As the tide begins its slow rise once more, the shoreline shifts. Water fills the cracks between rocks, and crabs retreat to higher ground or deeper crevices. Their claws remain poised, ready to grasp food items carried by the rising water. They return to their patrol, navigating the border between land and sea with purposeful confidence. Their silhouette against the wet sand appears almost harmless, small, compact, and familiar. But familiarity breeds complacency, and complacency near these armored foragers leads to injury. The lesson they offer is not one of fear, but of respect. Crabs are not villains, nor are they toys for amusement or props for photographs. They are powerful, essential components of coastal ecosystems, armed with claws capable of causing severe harm when mishandled. To share the shoreline with them safely, one must treat them with the same caution and admiration granted to larger predators. The rule is simple, written by the experience of countless injuries. Give crabs space, handle rocks carefully, and never underestimate the crushing force hidden within. Those compact, unassuming claws. Along the rugged edges of temperate coastlines where cold currents surge against stone, the underwater world takes on the appearance of an ancient fortress. Granite cliffs drop into shadowy chasms, boulders lie scattered like battlements toppled by storms, and kelp forests sway above like flags in a steady wind. Light filters down through fronds and fractured rock passages, creating narrow corridors of illumination that shift with every ripple of surface water. Within these natural structures, the silent engineers of the crevice realm guard their territories with armored patience. Lobsters, often seen only as foods on a menu or mythical beasts of the deep, are in fact powerful invertebrate predators with the capacity to defend their homes using crushing tools that evolved over millions of years. Their claws, oversized and muscular, grant them the ability to dismantle prey, shatter shells, and, when provoked by careless hands, inflict injuries severe enough to require medical intervention. Descending into their world reveals details that escape casual swimmers drifting above. The seafloor near rocky coastlines is carved into labyrinths of tunnels formed by natural erosion and wave action. Each crack, hole, and overhang becomes potential real estate for a lobster seeking refuge from predators and harsh currents. A fully grown lobster, often weighing several kilograms in colder regions, chooses these tight crevices deliberately. Their bodies are built for the job, elongated and armored, with articulated segments that allow them to wedge themselves deep into tunnels, leaving only their antennae and the tips of their claws exposed. The antennae act like sensory whiskers, constantly moving, sampling the chemical messages drifting through the water. They detect approaching threats long before any diver or predator sees them. Lobster vision, while not sharp in the human sense, is remarkably well suited to the low-light environment of the seabed. Their compound eyes pick up subtle movements and shifts in brightness, helping them identify intruders entering their territory. These animals are not passive residents. They are territorial defenders capable of explosive reactions. The claws of a lobster are not symmetrical tools. One is typically a crusher claw, with thick molar-like ridges designed to break hard shells. The other is a cutter or pincher claw equipped with sharp serrations capable of slicing. Together, they function as a dual weapon system that rivals the bite force of some small vertebrates. While divers often marvel at the size of these claws, they rarely appreciate the mechanical advantage they represent. The crusher claw can exert forces powerful enough to crack large clams, crush snail shells, and dismantle crabs. Marine biologists studying these forces have measured pressures that easily break wooden dowels and can leave deep bruises on thick gloves. For bare human skin, the damage can be immediate and severe. Fingers caught between the closing edges of a crusher claw endure a combination of bone-compressing force and tearing pressure. The injury is not simply a pinch, it is a crush, a mechanical trauma created by muscles evolved specifically to process armored prey. The greatest risk arises not when observing lobsters from a respectful distance, but when humans attempt to reach into their hiding places. Recreational swimmers and amateur divers sometimes explore the rocky shallows without understanding how efficiently a lobster can defend a home. They see a dark hole, perhaps imagining a harmless curiosity or a shell to examine. When a hand enters the crevice, the lobster responds instantly. From its perspective, a large, unfamiliar object has invaded its refuge. The lobster lunges forward, clamping down on whatever it can reach. Because the entrance of the crevice restricts movement, the trapped fingers or wrist become pinned between rock and claw, worsening the injury. The lobster, feeling resistance, tightens its grip, sometimes twisting its body in an attempt to pull the intruder deeper or force it out entirely. Injuries from such encounters include deep lacerations, broken fingernails, and fractured bones. The skin between joints tears easily under the shearing forces of a lobster's claw. Blood fills the water quickly. Although the underwater environment dilutes it enough to appear faint, the real danger is the depth of the wound. Lobster claws often puncture down to ligaments, and bacteria from the seabed or the lobster's own feeding activities can enter the tissue. Because lobsters frequently scavenge decaying animals and inhabit muddy sediment, the microbes they carry can be aggressive. Infections from lobster injuries require careful cleaning and, in some cases, medical attention with antibiotic treatment. Professional lobster harvesters understand these risks intimately. They operate with specialized training, using techniques built on generations of experience. Their handling methods involve grasping the lobster behind the claws, using thick gloves made from synthetic fibers designed to resist punctures and abrasions. Even so, professional fishermen occasionally sustain injuries when large lobsters manage to rotate or slip free. On commercial boats, workers develop a healthy respect for the animals they harvest, knowing full well that mishandling a large adult could result in severed tendons or crushed fingers. The professionals also know the importance of approaching the animal from behind, never from the front, where the claws have full reach. Lobster pots, engineered traps placed on the seafloor, pose their own risks to inexperienced swimmers. These cages often rest near rocky outcrops or sandy patches not far from shore. Curious divers sometimes approach them, peering inside to see the lobsters crawling around the bait. The problem arises when someone attempts to reach into the pot, either to free a tangled rope or to examine the catch. The confined space maximizes the lobster's defensive advantage. With no room to withdraw, the lobster can strike with accuracy and force, clamping onto hands or forearms with nowhere for the trapped person to move. Removing a claw grip while underwater becomes a challenge, requiring calm decision-making and careful leverage. Panic leads to thrashing, which only tightens the claw's hold. The defensive nature of lobsters is deeply rooted in their ecological history. For millions of years, they have survived by dominating crevices and using their claws to deter predators. Their exoskeleton, composed of chitin reinforced with minerals, provides armor but is vulnerable during molting. When they shed their shell to grow, they take refuge deep in rocky cavities, using whatever strength they still retain to repel curious fish. This evolutionary cycle reinforces their defensive tendencies throughout life. Young lobsters learn quickly that any object entering their immediate space may be a threat, and this instinct persists into adulthood. From an ecological perspective, lobsters are more than powerful crustaceans with strong claws. They play a vital role in shaping underwater communities. By preying on mollusks, small crabs, worms, and various benthic organisms, they regulate population dynamics and influence the composition of seafloor ecosystems. Their feeding habits help prevent imbalances that could destabilize marine environments. They also serve as prey for larger animals, such as large fish and octopuses, creating a dynamic flow of energy through the food web. Their crevices serve as micro-habitats for smaller organisms, seeking protection from currents and predators. Lobsters are thus not just inhabitants of the rocky sea floor, they are engineers of its complexity. The beauty of observing lobsters in their natural habitat lies in understanding their behavior, rather than interacting physically with them. Divers who approach slowly, maintain proper distance, and view the animals with respect often witness scenes rarely seen by casual swimmers. A lobster emerging cautiously from its den reveals the precision of its movement, antennae testing the water, claws opening and closing reflexively, tail segments ready to propel the body backward in a powerful escape jet if danger appears. These details illustrate a creature perfectly adapted to the challenges of its environment. Observing these interactions provides far richer experiences than attempting to handle the animal. The greatest misconception among inexperienced swimmers is assuming that lobsters, being slow when walking and prehistoric in appearance, are harmless. The truth is that a lobster is a highly capable defender, relying on reflexes, leverage, and sheer force. Its claws are the culmination of evolutionary pressure, favoring strength and versatility. While they do not pose the same level of threat as venomous marine creatures, the injuries they cause are mechanical, severe, and often long-lasting. Casual swimmers do not recognize the danger until it is too late. The lesson for anyone entering lobster country is straightforward and deeply practical. Exploring crevices is best left to professionals who understand the risks and have the proper equipment. Reaching into underwater holes, especially in regions known for lobster populations, is a gamble that can end in sudden pain and serious injury. Admiration from a distance offers all the reward with none of the danger. Professionals who harvest lobsters safely do so because they treat the animal with respect, using safely designed traps, heavy gloves, and controlled movements. Their methods should not be imitated casually. In the underwater fortress where lobsters live, power is not announced with aggression. It lies hidden in the quiet readiness of claws that evolved to dominate narrow spaces. For humans, the safest experience in this world is to remain an observer. The rocky sea floor, illuminated by filtered sunlight and patrolled by these armored custodians, remains a place of awe and biological precision. To appreciate lobsters fully, one must recognize the danger they represent not out of malice, but out of evolutionary necessity. They defend their homes with tools strong enough to crush, slice, and hold, and they do so with instincts honed across countless generations. The message is clear and simple, carved into the logic of nature itself. Admire lobsters from a respectful distance, keep hands out of holes and traps, and remember that beneath the calm shell of this ancient crustacean lies a power that can turn a moment of curiosity into a lasting wound.